everyone, and I should thank the organizers for giving me this opportunity to talk about some of the work that I and many of my collaborators have been doing over the past few years. So, I am going to give somewhat of a general overview of the motivations that drive us to do what we do in the first half of my talk, and then I will go into the more technical details of what we have been doing in the second half. So, that is the plan. So, okay, I guess all the years have been cut out, but these are the references that I will be talking about, in the these are many of my collaborators. Okay, one is, yeah, that's for you to guess. Sorry, I think it got cut off. Sorry. So I think so the last two ones are last year, and the one before is 2021, and then the one before that is 2020. Yeah, yeah. So anyway, so I want to kind of basically talk about two different things, okay, which are the basic things. One is that what is an open quantum field theory, since one doesn't hear a lot about open quantum field theory, and why do we want to study it? Why should one be interested in studying it? So that's what I want to kind of tell something about. And then I want to say why holography or gauge gravity duality, sorry for the typo, or ADS-CFT, how does it help? How does it help in the study of open quantum field theories, and what does it tell us? Okay, so that's a basic goal. So let me just start without much ado. So let's start with by explaining this title of open quantum field theory. So here the adjective open is like when we say open system versus closed system, and by open quantum field theory, what I mean is a quantum field theory which is in contact with some environment, okay, some other field theories, which you want to kind of integrate out, so to speak, okay, whose effects you want to integrate out. Okay, so this is a very familiar thing in quantum mechanics, where, for example, you can think about some spin which is in some thermal environment, or so what happens is that the system evolution is no more unitary, but it is affected by the environment. Okay, the full system and the environment, of course, evolve unitarily, but the system alone doesn't evolve unitarily, but so then the question becomes, how does it evolve, and how should we think about this evolution, and can we write down some effective field theory which kind of integrates out the environment, just to give description purely in terms of the system, and when is that such a description possible, and when such a description is possible, what form does it take? These are the kind of questions that one kind of thinks about. Okay. Another example which is probably good to think about is a classical example, which is a Brownian particle in a fluid. Okay. So this is very old and textbook example in non-equilibrium stat mech. Okay. So what does Brownian particle is an open system, it's a classical open system which is coupled to the fluid around it, and what we know physically is that from looking at it is that it feels a Stokes drag, okay, because of the viscous hydro. It's like you think of it as a sphere of a finite size, then the flow around that sphere, as we learn, gives rise to a drag. Okay, so what happens is that the Brownian particle motion has a drag force. Okay, so there's a drag force. There's a which can be modeled by, let's say, a linear in velocity, but it also feels a noise in the sense that it kind of is kicked around. Okay, in the sense that there's some random force on it, which is the point of the Langevin theory, and which kind of comes from eventually from the microscopic motion of, let's say, the water molecules or the fluid molecules or whatever it is. Okay, and Einstein and Smoluchowski more than 100 years ago, okay, pointed out that these two effects are very closely related, okay, which is the notion of the fluctuation dissipation theorem. Okay, and this is a kind of a very like a characteristic set of statements for open systems. So, what happens is that when you have a system which is open, it kind of dissipates, okay, and then it also feels some noise. Okay. So, these are two main aspects of open systems which I want you to keep in mind. Okay. So, now moving on from classical systems to quantum systems. So, how do we think about open quantum systems? It's kind of somewhat similar, okay, just that you have to think a bit more abstractly in terms of a formalism which was developed in 1960s by Schwinger and Keldysh independently, Feynman and Vernon, and kind of explicated really very well by Caldera and Leggett. So this is a series of very landmark works which kind of try to understand open quantum systems, and the point is that so there is a formalism to do it which is kind of old, and which kind of to some extent is almost as old as a lot of things in field theory. Okay. So what is new? So what is new is that that these formalisms in open quantum systems have seen a lot of if you want a renaissance, so to speak. Okay. They were never forgotten really, but I think over recent years, recent decades, people have started thinking about them more and more sharply and more accurately, and trying to think about these limits and the kind of questions that I was asking. Okay. Mainly I think motivated by two different concerns. One is that one is a standard realization that to understand how classical physics emerges from quantum mechanics, you need to understand open systems, because classical systems by definition are open systems. Open quantum system it's only when quantum systems are open to the environment, okay, they kind of become classical and they behave classically. Okay. And it's only the in one sense it's the entanglement with the environment, okay, which makes them not entangled with other things and start behaving classically. Okay. So that is one kind of way to think about open quantum systems, why open quantum systems are interesting. If you want to understand how things become classical, okay, then you should think about open quantum systems. And another thing which is that's just a formal question. As a theorist you can ask why is classical mechanics true, when is classical mechanics true, and then you will be naturally led to thinking about open quantum systems. But there is also an experimental motivation, in the sense that the experiments have become better and better to kind of design what I call as controllably open quantum systems. So of course you might think it's very easy to realize experimental open quantum system. Just look around, everything is an open quantum system, right? Okay. So in fact closed quantum systems almost never exist in the real world. They only exist in textbooks and so on, right? So it's very easy to at one level it might be, you might think it is very easy to realize open quantum systems. So experimentally it's just very easy to study them. But a little bit more thinking tells you that that's a bit not quite right, because yes, open quantum systems are ubiquitous, everything you see is open quantum system, but to really study them experimentally you need to be able to control it, in the sense that you need to be able to control how they are interacting with the environment. Let's say somehow tune the coupling to the environment, okay, and see how the behavior of the system changes as you change the coupling to the environment. Does it become different when it becomes strong, weak, and so on and so forth, and that we cannot do usually. Okay. So that is why it is to study open quantum systems it may be a bit of an oxymoron, but it's true statement to say that first you have to get a good closed quantum system, and then you have to controllably couple it to the environment, okay, in a way that controllable in the sense that you can the coupling to the environment is completely under your control, you can tune it and then study what happens experimentally, and the experimentalists over the past decade or two, okay, have been able to get there more and more with more and more systems, and that has also led to a lot of new questions, I think, in this field of open quantum systems. Anyway, so what I wanted to talk to you about is not quite open quantum systems, but about open quantum field theories, okay, where we do not have the experimental control at that level. Okay, we do not have quantum field theories where, so the quantum field theories, we all the time talk about quantum field theory which become classical, like electrodynamics, fluid dynamics, whatever have you. Okay. But like we do not have, so they are all coupled to the environment, they are all open quantum field theories. Okay. All classical field theories eventually in real world are open quantum field theories, but that by the same kind of logic I was saying is not enough to kind of study them experimentally, and what you need is controllably open quantum field theories, and we don't have them at least at present, but we probably will get there. But that's the kind of like motivation that I'm talking about. Okay.
I have a question.
Yes.
There could be also another way to engineer open quantum systems, is just to do some post selection. So you do for every step you kind of post select or measure, and then that evolution is of course not unitary because of the post selections that you're doing, and that way you can drive the open quantum systems to often some new kind of.
Sure. But you see, but the point is that like I'm making is that you can do all these things, but you have to first get a closed quantum system to experimentally, because if your system is uncontrollably interacting with the environment, you can do measurements and you can try to control it, but then there are other things which are happening which you don't know what is happening, right? Okay. So unless you can control for it, like it is very difficult to say experimentally study that if you do this you will get it. Right? Okay, because whatever you get might be because of the post selection or measurements you did. It might also be because of just interacting with some environment in some way you don't know. Okay, right? So that's all I'm saying. So you can do all these things, but the important thing is to first get like a very like good closed quantum systems, and then control the way they couple to the environment. That's what I'm saying. Okay, so okay. So let's move to this open QFTs. Okay. So at this point, like from an experimental point of view, these are still very difficult to study. Okay, because of the reason that I just mentioned. I'll also tell you in a moment why they are also kind of difficult to study theoretically. Okay, but let's just start thinking about open quantum field theories. Okay, so what are open quantum field theories? So just like extrapolating from the Brownian particle example that I told you about. Okay, open quantum field theories are field theories which exhibit both dissipation and fluctuation because they are coupled to the environment. Okay, now you can ask, okay, what are such field theories which do that? Okay, which we know. Okay, one of the oldest field theories that we know, okay, historically, actually does this. Okay, at least like for example, fluid dynamics is dissipative, right? If you take a cup of water, you stir it, you wait, at some point like it stops rotating, right? Okay, so the energy that you put into the fluid just dissipates and disappears. We now know it goes into the microscopic degrees of freedom. Okay, and so like this is an example, a very common example of a dissipative field theory, and hence an open field theory. Okay. Now what about fluctuations? Now we don't often talk about fluctuations, like in fluids, unless you are thinking about turbulence and so on and so forth. But the point is that even in a non-turbulent, just a fluid which is at rest, just a glass of water which is at rest, there are actually fluctuations. Okay, because it's just a thermal system. Okay, and if you want, it is kind of like going over all the states in an ensemble. If you want to think about it that way, it's just a thermal state which kind of is ergodically going through all its microstates. So there are just fluctuations associated with it. Okay, there are like so real fluids always have fluctuations, and this kind of like means that what we should really be talking about are fluctuating hydrodynamics. Okay, rather than just talking about hydrodynamics, which are dissipation. Okay, like there are also fluctuations in hydrodynamics, and one of the like holy grails in this thing is to kind of try to understand and characterize what are the fluctuations in hydrodynamics. Okay, so if you want to think about hydrodynamics as an open quantum field theory with dissipations and fluctuations, you can ask a question: can you characterize, okay, precisely like what will be the kind of fluctuations that are there and what will be the kind of dissipations that are there, you know, like and how are they related, and does it depend on which fluid you're talking about, how does it depend on which fluid you're talking about, and so on and so forth. Okay. One thing, for example, high energy theorists might be interested in is that you know, in something like quark-gluon plasma, okay, which you form in, let's say, RIC or LHC or something, okay, you can ask, you know, like when we have fluctuations of that quark-gluon plasma, how does it show up in the particles that come out, okay, when this quark-gluon plasma kind of freezes out and then hadronizes. Okay. So that's kind of another question one would like to answer. Okay. And the question and the point here is to try to kind of understand this in a systematic way by an effective field theory point of view. Okay. Rather than, you know, like so usually when this kind of question is asked, so what people do is that, you know, they try to do some kinetic theory, okay, which is fine, you know, like assuming that things are weakly coupled. It's not quite clear that quark-gluon plasma is weakly coupled, okay, but assuming that it is, you know, like at least in the regime of hydrodynamics, you can try to say something, and you can say that maybe even if it is not weakly coupled, maybe kinetic theory will tell you something roughly about, you know, like hydrodynamics and deviations from hydrodynamics and how the hydrodynamics comes about and so on. Okay. Yeah. Not necessarily. Okay. So the fluctuations can be thermal, they can be quantum fluctuations. Okay. But all the time the point is that the fluctuations come about because you have a system and you've integrated of the environment. Okay. And it's at the end of the day, it's some characteristic of the things you have integrated of. In the fluid mechanics, the things you have integrated on are not some outside environment often, but it's just its own microscopic degrees of freedom to get some effective fluid description, where you have just forgotten about the individual water molecules and you're now talking about the velocity field, right, temperature field and so on. So the question is that, so the fluctuations then are, you know, like are something about the microscopic degrees of freedom. If they are thermal, they are expected to be somewhat universal. Okay. But even that, beyond linear response, okay, I think, you know, like we do not know in what sense they are universal and what sense they are not, and so on. Sorry for that. You know, like yeah. Okay. Anyway, so that's something that one to think about. Okay, about fluid dynamics. Well, okay. I have not defined precisely what I mean by fluctuations. So what I mean by fluctuations in this system is something which is not a unitary evolution, okay, which you can think of it as some kind of a stochastic force, like in the case of Brownian particle. If you define it that way, actually closed systems cannot have fluctuations because closed systems evolve unitarily. Okay. But you could define fluctuations in some other way. You could think of it as some standard deviation of something, okay, some operator, some observable, which of course can be there. There's some uncertainty and so on. Okay. But if you kind of define it as you know, something which leads the system to deviate away from exact unitary evolution, okay, then by definition, you know, but I agree with you that fluctuations are sometimes defined not that way. Okay. So yeah. So there's a question of what do you mean by fluctuations itself here. Okay. But if you think about it from the Brownian particle, what I mean is some kind of a noisy, stochastic kind of external source. Okay. Okay. So that's an example one. Okay, which why you should be interested in open quantum field theories, because you know, like because of fluid dynamics and fluctuating hydrodynamics and how you should think about them and so on. This is a kind of a second example, okay, which is also something that I'm interested in, though I won't talk to you much about it today in this talk. Okay, so which is about cosmology. Okay, so in cosmology we know that our standard model of cosmology has this picture that you know, like that the universe expands, and as universe expands, there are modes which were, you know, like within the causal contact, okay, which kind of go out of causal contact, and they kind of also re-enter. Okay, and the point is that, you know, like so there's a constant loss of accessible information from the point of view of an observer sitting in the universe. Okay, so a cosmological observer. Okay, and so there's a question of dissipation, which is that like you're constantly forgetting things. There's this forgetting in steroids is inflation, where like everything is forgotten, lot of modes just exit the horizon. Okay, and that is supposed to explain many of the features that we observe about CMB and the fact that we don't observe monopoles and things like that, right? Okay, so the point here is that like cosmology has these things that the field theories in cosmology are also dissipative in this sense that the information is constantly lost due to the expansion of the universe. Okay, and they are also kind of fluctuating. Okay, there are also fluctuations. In fact, like the standard model of cosmology says that again there were fluctuations which are produced during inflations, which then seeded all that we see today. Galaxies, us, everything actually came by some quantum fluctuations which are seeded at the end of the inflation. Okay, so the point here is to kind of like understand systematically, okay, how to think about this, and I think like how to think about this should also be phrased in terms of open quantum field theories, especially if you are kind of thinking about actual observables observed by an observer who can only access a particular part of the universe. Okay, so I will not talk much more about it today, but I think it's a very extremely important thing, and if you want to talk about it, I can tell you more what I think about these things after the talk. Okay, so this is an example 2, physical motivation, why we should think about open quantum field theories. Okay, a third example, which might be close to many of your hearts. Okay, is about black holes. Okay, so the point here is that like of course black holes have dissipation. There are things falling into the black holes. Okay, from the point of view of the exterior fields, there are things constantly falling into the black hole and lost to the exterior. Okay, and the fluctuations, okay, in the case of black holes are just Hawking radiation, where the black hole fluctuates and emits like some kind of radiation back into the exterior. Okay, and the point here is that like how you should think about this system and how you should think about like the field theory in the exterior, and you can ask, can you just write down just an effective field theory of just the exterior? Can you somehow integrate it out the interior of the black hole, okay, and write down an open quantum field theory of the exterior, okay, which will kind of tell you like both about things falling in, things that are lost to the exterior, as well as things that are that come into the exterior. So in some sense the exterior itself is like a Brownian particle which is kicked around by the Hawking radiation and which loses energy into the black hole. Okay, and the question is that like can you have an exterior open effective field theory, okay, which describes these things. And one of the things that has come out of various things that I'm going to tell you about in the later part of the talk is that you can indeed do that. Okay, and in fact this problem is very closely related to this example 1 of hydrodynamics, okay, by ADS-CFT correspondence, as I will say this thing. So the question is that like so how do you think about them? Okay, now how do you think about so what you have to do at a nonlinear level is that you have quasi-normal modes which are falling into the black hole, you have Hawking modes which are coming out, and you have these things scattering. Okay, maybe then they scatter into some some combination of Hawking modes and quasi-normal modes. If you have like various kinds of scatterings, then the question is that how do you think about it? Okay, because most of the time when we think about Hawking radiation, we think about it in terms of free field theories in kind of collapsing or black hole backgrounds, but what happens when you add interactions? What happens to the Hawking radiations when you add in interactions, and how does it work? Let's say you take 5-4 theory, then how does it work? like if you also include 5-4 scattering. So this is a kind of question that one will be interested in. Okay, and we'll see soon that this is very closely related to what happens in the hydrodynamics. Okay, so let me kind of like now move on to some of the more technical details. Okay, so the question is that like so how do you kind of model these things? Okay, so one example is exactly what I said. Okay, which is that you can just like start with a particular CFT formulation which actually reduces to this black hole question. Okay, which is that like you take the CFT, okay, and you couple it to some field theory, okay, some weakly coupled field theory, let's say free scalar field theory, okay, which I denote by like this this psi, okay, So there's some free scalar field theory or some weakly coupled scalar field theory, which is then coupled to this to the CFT bath, okay, which is at some finite temperature T. Okay. Then what I want to do is to integrate out this bath, okay, and try to get an open quantum field theory, okay, for like for the field theory. Okay. So this is a kind of a model of an open quantum field theory, okay, where you have some weakly coupled, you take your favorite field theory, couple it to some CFT, okay, which is kind of like at finite temperature, which and then you kind of integrate out the effects of the CFT, and you can ask like how does the effective open quantum field theory work, and how do fluctuation and dissipations and various physics that I was talking about work in this example. Okay. If the CFT is actually a large and strongly coupled CFT with some holographic dual, okay, you can then map this open quantum field theory problem to the problem of this Hawking radiation I was talking about in the previous slide. Okay. So what happens is that like this scalar field, this probe scalar psi, then couples to some kind of an operator, say some single trace primary scalar operator in the CFT. Okay. So corresponding to that, there is a scalar field in the bulk. In the ADS black hole background. It's a black hole because you have a finite temperature, okay, and what you want to do is that like so to understand, okay, how this probe field theory, okay, fluctuates and dissipates due to its coupling to the CFT. This problem by ADS CFT gets mapped to the problem of how a scalar field in the exterior of a black hole, okay, fluctuates and dissipates because of its vicinity to the black hole. Okay. It fluctuates because the black hole is constantly sending in Hawking radiation. It dissipates because things are falling into the black hole. Okay. And the problem of this open quantum field theory of this exterior is related to the problem of thinking about the open quantum field theory of a field which is outside the CFT, which is coupled to the CFT. Okay. They are not the same problem, but they are related. Okay. And the point is that like how do you kind of do these calculations. So one of the things that has made these kind of calculations possible, okay, within the ADS CFT, within holography, are these ideas, okay, by Skenderis, Van Ries, and Crossley, Glorioso, and Liu recently, and basically the idea, as I will explain, is to kind of like think about the path integrals which kind of define open quantum field theories, and then kind of implement them on the gravitational side in a specific way, as I will say. Okay. But I mean I'll come to the technical details in a moment, but the point here is that once you kind of use these ideas, okay, you can actually design like you can actually simultaneously answer both these questions of like what happens for like some kind of a field theory which is coupled to CFT. Okay. You can also ask this question where you have a CFT itself has a quark-gluon plasma. Okay. It has hydro, and you integrate out the internal degrees of freedom of the CFT, the microscopic fast degrees of freedom of the CFT, to get hydro. What happens? Okay. And all these questions on one side get related by ADS CFT to kind of questions about like black hole and exterior open AFT. Okay. And the very good thing about the holography, okay, which is what I want to say, is that in some sense black holes are very good baths. Okay. In general, strongly coupled field theories are very good baths. Okay. And the lack of these very good baths, okay, let me maybe pass a bit and try to explain why you need a very good bath to actually design an open quantum field theory theoretically. Okay. Now what happens, so when can you integrate out like an environment? Okay. So for example, if you think about, let's say, a pendulum which is moving in air, okay, you can ask when can you write down an effective motion equation of motion, okay, for the pendulum. Okay. So we usually kind of describe the pendulum by some kind of let's say damped harmonic oscillator. The question is that when can you do it? Okay. You can do it, okay, if you think about it a bit, you can do it if you're provided the environment actually like is has a dynamics at very faster scales than the system itself. Okay. For example, you can do it for an ordinary pendulum moving at ordinary speeds through the air only because the air molecules are moving very fast. Okay. And as the pendulum swings, and let's say it swings one period and comes back, okay, the air has completely forgotten, okay, what has happened in the previous swing. Okay. Basically, like that's why you can basically write down that every time the pendulum swings, it kind of meets the air as if the air didn't know that the pendulum did what pendulum did in the previous period, because within a one period of the pendulum, so much dynamics has happened in air. Okay, the air molecules have scattered among themselves so much that they have kind of forgotten, okay, any kind of memory they might have had from the previous swing. Okay. Which means that you can write down some kind of a local what many people would call as a Markovian evolution equations for this pendulum, because in some sense every time what matters is not what the pendulum did one period ago, but what the pendulum is right now doing. Okay. The environment doesn't have a memory. Okay. An environment doesn't have a memory if the dynamical time scales in the environment are very, very fast, as happens in this example. Okay. And when that happens, okay, and the system is moving very slowly, you can try to kind of integrate out the environment to write down an open effective field theory for this. I mean, this is a standard notion of effective field theory, where that you have to integrate out fast degrees of freedom, you have to keep the slow degrees of freedom, okay, and there should be a hierarchy. Okay. Only then you can get an effective field theory. So this is a standard effective field theory wisdom, okay, which holds true even for open effective field theories. Now, if you think about it, so you need a bath which kind of forgets fast, okay, and weakly coupled baths do not forget very fast, okay, because okay.
Are you saying that you get Markovian dynamics always in this kind of macro systems?
Yeah, I mean, provided what I'm saying is true, that you're looking at a correct kind of observables. Yes.
So I'm a bit confused here, because typically in this black hole cases, relaxation times are ordered temperature.
Yes.
Set by the temperature.
Yes. Inverse temperature. Yeah.
Yeah, inverse temperature. Sorry. So in that case, but the system on its own will have some kind of.
Yeah. So you can write down open effective field theories only if when the system is moving very slowly compared to that time scale. Yeah.
So which means that you are very restricted class of systems you can couple, only fluids or something.
No. Okay. Yeah. So that's the thing. The point is that if you want an open effective field theory, but this is a standard effective field theory, right? You need a hierarchy to have an effective field theory. Okay. I'm just saying the effective field theory wisdom, and only then you can, or else you have to keep track of the full system. Okay. You can't integrate out. Okay. You can integrate out only when there's a hierarchy of time scales.
Yeah, my question is basically in what practice, can you give some concrete example where you can actually have this hierarchy or context of a black hole?
Yeah, for example, you can take this guy, okay, and you can just, if the external field theory, okay, is kind of you're only interested in dynamics of external field theory at time scales when it is moving very slowly, okay, you can do that. I mean, another example is just the pendulum example, for example. Okay, I mean, if a pendulum is moving as fast as air molecules, you can't treat it as a damped harmonic oscillator.
So what do you want to tune in the? So you want to tune the mass of the field, like you got a very heavy particle or heavy.
You can.
The couplings,
So you want to keep all the time scales slow. So whatever it determines the time scales of the theory, right? Okay. So, I mean, yeah. So the statement I'm making is that you need kind of a hierarchy between the time scales of the bath and the time scales of the system to kind of treat the system as an autonomous thing, like a damped harmonic oscillator. Okay. If a pendulum is moving as fast as air molecules, you cannot describe it as an open system, okay, as an effective open system, because then it would matter. Then maybe pendulum just made a vacuum when it swung one way, and the next swing, okay, will know that there is a vacuum which was created by the previous swing, which will affect the pendulum's motion in some complicated way, okay, non-local in time, okay, and then you have to take all that complicated things into account, okay. We usually don't worry about it, because whatever vacuum the previous swing created, all that has been washed out, okay, by the time the pendulum comes again, okay, because the air molecules move much fast, okay, and that's the point. So if you think about it, so what you need is baths which kind of do dynamics very, very fast, and weakly coupled systems do not have fast dynamics, because they scatter less. Okay, if it is an ideal gas, then the scattering takes a long time. Okay, you can still have like things. I mean, actually air is not strongly coupled, but it's just the pendulum is even more slower. Okay, than the air collisions. Air is almost an ideal gas, but the pendulum is even more slower compared to the scattering time scales of the air. Okay, and that's why like this works. And what you need like to kind of theoretically make a good models are things which are kind of have a lot of scatterings, and that means that you need something which is very strongly coupled. Okay, people who have thought about thermalization, for example, okay, know that there's a similar kind of statement about thermalization, that very good baths are usually kind of decently strongly coupled, and if they are weakly coupled, you have to kind of study them for non-perturbatively long time scales. Okay, somehow you should resum things and do various things before you can understand this kind of dynamics. Okay, and that is the basic thing, and that's why like thinking about black holes is very good, because as Ian pointed out, okay, the time scales here are just of order inverse temperature. Okay, and that is good. Okay, which means that anything which is it's not much smaller than that. Like in a weakly coupled system, usually you have inverse of coupling times inverse of temperature, and if the coupling is very small, you get very long times. Okay, but because these are strongly coupled from the point of view of CFT, and because these are black holes from the point of view of gravity, they are very good baths. Okay, and that's why like thinking about open quantum systems, quantum field theories in this context, one can make much more progress. Okay, because here it's just a question of solving things and doing this. I mean, this is kind of is an extension of this old idea that viscosity is easy to model in ADS CFT, right? Like thermalization is easy to model in ADS CFT, because like you're thinking about a strongly coupled field theory, and where viscosity and things like that are very well defined, and the dual is a black hole where also things are very well defined. Okay. So let me kind of like say a bit more, and let me kind of move on, since I'm kind of already half an hour into the talk. Okay, let me kind of focus more into the particular kind of things which relates this fluctuating hydrodynamics and the exterior open EFT in the case of the black hole. But before that, are there any further questions? So this is kind of my end of the overview. Yeah. Q15 curve space-time, and what is this? In de Sitter. Well, that's related to the cosmology, okay, which I have decided I won't talk about this talk because it will completely derail me. But I'm definitely interested in that question, so I can talk to you later. Okay, de Sitter has its own, yeah, it's very interesting, but yeah, but different from what I want to talk to you about. But okay, anything else? Yeah. So by late radiation, now you're thinking about some kind of a black hole which is evaporating and so on. Okay, so then, well, yeah, sure, but I do not know, like really, okay, because that's a more difficult question than what I'm answering. I'm thinking about just a black hole in equilibrium, say large ADS black hole in equilibrium, okay, and you don't open the boundary and so on and so forth, okay. You can ask what happens if you drive, open the boundary and drive it to very non-equilibrium, like people do when we think about Page curve and so on. Okay, there, of course, at some point, the Hawking radiation, as we, if the black hole information paradox has to be solved, should contain a lot more information. Okay, and then it's not even clear you should really call it fluctuation, because at some point it's just very correlated with what is happening. Okay. So I do not know what is the best way to think about it, just from the point of view of open quantum field theory. But yeah.
So then I get some effective limit for second scale. So like how this in open quantum system?
Well, what happens in open quantum systems is that you have to integrate out. I mean, the general principle is still true, that you have to integrate out fast degrees of freedom to get like effectively slow degrees of freedom, but it's not always the massive guys which are the thing. If you think about the pendulum, okay, the thing we are integrating is air molecules. Okay, the air molecules are not much more massive than the pendulum ball. Okay, but that's not the point. Okay, so we are used to thinking about just things in terms of the mass because we think about vacuum field theories. But when you think about open quantum field theory, you should actually focus on time scales. Okay, and the point is not that air molecules are massive than the ball, the gong. Okay, but the point is the air molecules move faster, right? And that's why you can integrate them out. And yeah, so you have to kind of like the effective field theory still applies. Okay, but you have to kind of think a bit more carefully. And in details are different than in what happens in vacuum field theories and Wilsonian paradigm there. Okay. Okay. Yeah.
Just a quick clarification, just to make sure that I'm understanding. Is it the case that when the path is strongly coupled, the effective action in terms of the psi field is local?
Yes.
And if not, then it can develop some non-local?
Yeah. In general, it will be non-local at time scales of the bath. Okay, and just the time scales are smaller if the bath is strongly coupled. Okay. Okay. So. Okay, so the point here is that so this is a bit more about like how these two problems are related about this hydrodynamics and open quantum field theory. So the question is that the point here is that you have energy fluctuations in hardly coupled plasma. Okay, and you can think about fluctuating hydrodynamic which describes it, and you can also think about Hawking radiation. Okay, of gravitational waves in the case of ADS black holes. Okay, and the statement is that the ADS CFT tells you that the effective field theory describing these two systems are the same. Okay, and hence the fluctuating hydrodynamics is same as the exterior EFT of gravitational waves. Okay, maybe I can just stand here. Okay, so let me just go through these things quickly since I'm kind of running out of time, but the point here is that so let me just review what about slow and fast degrees of freedom. Okay, in the case of what happens with black holes. Okay, so this is probably old story to many of the senior people here, but let me just say it, this thing. So there's a thing called fluid gravity correspondence, which basically tells you that that the gravitational physics on the bulk ADS side is dual to some kind of fluid dynamics of the quark-gluon plasma of the CFT side. Okay, and what happens is that so this is mostly thought about in the case of without Hawking radiation, where you just think about dissipation. Okay, where on the black hole side you just think about modes which are falling in, which are the quasi-normal modes, and then you think about only purely dissipative hydrodynamics on the CFT side. Okay, so this is the fluid gravity correspondence. Now why there's one way to think about this fluid gravity correspondence, which is that which is basically the statement that when you have modes which are falling into the black hole, okay, there are kind of modes which fall in very quickly, and there are modes which take a long time. Okay, so one kind of heuristic way I like to think about this is this old kind of picture, I think originally due to Newton. Okay, where Newton basically argued that there's a relation between how you throw things. Okay, and when you throw some ball or something, how it falls is related to how the moon goes around the earth. Okay, the ball has a small time scale, okay, by which its dynamic gets over, whereas the moon goes around and around for many centuries. Okay, and the basic thing is that to go from a moon, or maybe in the modern language some kind of a satellite, is that you have to give it a more horizontal velocity. Okay, so if you give it a more and more horizontal velocity at some point, okay, you get a very long time scale dynamics. Okay, in the gravitational thing, and something very similar happens with ADS black holes, in the sense that if you kind of throw gravitational waves, okay, which are just radially falling in, okay, they just fall in very fast. Okay, but you can think of gravitational waves or electromagnetic waves which are kind of have more horizontal velocity, so to speak. Okay, they move more and more horizontally, they take more and more time to fall, and in some sense the perfectly horizontal guys take the longest time to fall. Okay, the kinds which are the waves which are just grazing, if you have a horizon like this, and the things which are grazing take very long time to fall. And in fact, if you think about integrating out all these modes which are falling fast, okay, and only kind of write down an effective theory for the gravitational wave which are traveling very, very slowly. What the fluid gravity correspondence literature shows you is that what you get is that the slow modes, okay, the slow grazing modes actually obey Navier-Stokes equation, okay, which is the basic idea of fluid gravity correspondence, that the gravitational waves which are, if you integrate out the fast modes of the gravitational waves, fast quasi-normal modes of the gravitational waves, and you write down an effective field theory for the slow modes, okay, then what you get is hydrodynamics, okay, and this hydrodynamics is same as the hydrodynamics that you get on the CFT side, okay, where you have a clock-ground plasma and you have some microscopic modes. You integrate out the fast microscopic modes, then you get, you know, like a hydrodynamics of long wavelength this things, okay. So hence this long wavelength and very slowly falling quasi-normal modes, gravitational waves, okay, form an open system, okay, which are where the closed system is both the black hole as well as the fast falling modes, okay, and you kind of integrate them all out and you try to write down some effective theory which describes the long time dynamics of these slow modes, okay. So this is a statement about fluid gravity correspondence. Now what is often not appreciated, okay, is that you know that there is a similar statement about Hawking radiation also, okay, in the sense that the Hawking radiation also there is a slow Hawking radiation and there is a fast Hawking radiation, okay. So we always think of Hawking radiation as completely random thermal thing, okay, you throw in something very quickly the black hole thermalizes and, you know, like, and everything becomes thermal, okay, and that's what we think about Hawking radiation as. Actually that's not quite right, okay. What happens is that even in the Hawking modes there are Hawking radiation, there are Hawking gravitational waves and Hawking electromagnetic waves which come radially outwards, which thermalize very quickly, which kind of become thermal very quickly, but there are Hawking modes which are kind of grazing, okay, around the horizon, okay, which actually take a long time to thermalize, okay, in the sense that, you know, like if you throw in things, okay, you know, it takes a long time, okay, for them to settle in, very similar to what happens with hydrodynamics. The hydrodynamics, if you stir it, it settles in, but it still settles in very slow time scales compared to the microscopic time scales. Similarly, the fluctuations of the hydro are also, there are long-lived fluctuations of the hydro and there are short-lived fluctuations of the hydro. Similarly, there are long-lived Hawking modes of a black hole and there are short-lived Hawking modes of a black hole, okay. The Hawking modes, and the point here is that when you think about trying to write down an open effective field theory for these, you know, like long distance modes, hydrodynamic modes, what you have to do is that you have to kind of freeze, you have to write an effective field theory which describes both the slow infalling modes and slow outcoming modes, okay, slow Hawking modes, and then you write down an effective field theory for these things, integrating out all the fast guys, all the fast dynamics, okay, and that's what you should do, okay. So you have a long wavelength slow Hawking radiation which you have to keep, which you have to freeze.
Yeah.
So,
you're saying that there are two modes that those that go readily outward, those are the fast.
yes.
Then the ones that pass to like parallelly, those are the slow modes. So if I just do Hawking's analysis, how do I distinguish the two mathematically?
So Hawking's analysis is usually, the problem here is that Hawking's analysis is usually done with a spherical black hole, okay, and in the spherical black hole, you know, this the slow and fast are not as cleanly distinguishable, okay, because, you know, like everything is gapped, okay, everything has some time scale, okay. So but I think this is still true there, okay. It's just a standard gravitational dynamics, okay. One way to do it is just to solve the equations and see, okay, that you just see that, you know, there are slow modes, okay. It is a wavelength. In the sense, see, that's why, you know, like spherical black holes are a bit complicated, okay. The point is that if you have a very long wavelength slow modes, okay, they kind of die out very slowly. From a hydrodynamic, this is actually very clear, okay, in the sense that if you have let's say a diffusion, okay, if you have a very slowly varying, let's say, number distribution, it will take a long time for it to homogenize, okay. You know, if you just solve the diffusion equation, okay, whereas, you know, and its time scale is just set by the wavelength, not by the microscopic dynamics, okay, and longer the wavelength, slower it is, okay, and similar thing happens with the Hawking modes, okay, that the very long wavelength grazing Hawking modes, okay, actually die out very slowly, okay, relax very slowly. Their dynamics is very slow. Hmm? Sorry, the I'm not entirely sure, but this distinction is very clear if you have a planar black hole, and where you can actually talk about horizontal and vertical modes. You know, like yeah. So and the point is that, you know, like at least for the infalling modes, what I'm saying is very standard, you know, and very well known. Okay, and which is what leads to hydrodynamics. Okay, the only thing I'm saying is that the similar thing is true for Hawking modes also. Okay, and yeah. And the point is that the effective theory should take that into account. Okay. Yeah.
What do you mean by Hawking radiation and Hawking modes?
Any mode which comes out of a black hole, I call it a Hawking mode. That's my definition of Hawking radiation. It's a radiation that comes out of a black hole, rather than something which falls in. It's a quasi-normal mode.
The stress tensor when you take the expectation value and it's for that particular mode, and you take the projection or outgoing algebra will be non-zero or something.
Yeah, you can say it that way. Yes. Yeah.
You have a more precise definition.
No, actually, outgoing mode, I think this is a precise enough, right? The question is that whether it's outgoing mode or incoming mode. Infalling modes are quasi-normal modes. It's a question of what boundary condition they obey at the horizon.
Yeah, and then of course the spectrum also, whatever these properties will depend on what kind of boundary condition you are putting. Whether you put in transmitting boundary, transparent boundary conditions, or reflecting.
You're talking about the ADS boundary?
ADS boundary.
I just put standard boundary conditions. GKPW.
So you are just reflecting.
Well, it's not quite reflecting. It's a GKPW. It's a non-normalizable, normalizable, all that standard. So my CFT is a unitary theory. I don't want to play with it. Okay, I don't want to kind of, you know, yeah. My CFT is a bath and it's a unitary theory. I want to couple it to something else. Okay, but the something else is weakly coupled. Okay, so yeah. Okay, the point here is that, you know, like yeah. So the point here is that there are slow Hawking modes and fast Hawking modes, and what the exterior EFT should do is to kind of, you know, like write down an effective field theory for both the slow quasi-normal modes and slow Hawking modes, which are dual to writing down a field theory for slow hydrodynamic modes and slow fluctuating hydrodynamic modes.
So I should not think of it as like left moving modes for the
Left, right. You're thinking about Penrose diagram.
Yeah.
Yeah, you can think of it that way. But of course, the point is that once the modes, in general, the modes couple, it's a combination and they scatter and, you know, interacting theory. So this is a very, you know, I mean.
Part of right moving modes would be this slow modes.
Yeah. So eventually, what happens is it's like hydrodynamics, right? And what is the slow mode? It's not easy to say, but there is a slow mode. Okay, right? Okay. So let me just, you know, like I think I'm kind of running out of time. So let me just summarize what are the things that we could do. Okay, and what is the kind of thing you can do? How do you write down the effective field theory for this exterior open EFT, which also gives you an effective field theory for the fluctuating hydrodynamics. Okay. So the point here is what we have been discussing is to kind of cleanly separate the technical and the conceptual problem is to cleanly separate the slow modes from fast modes, integrate with the fast modes. Always in effective field theory, this is the conceptual problem, and the point is that, you know, like there's a way of doing it, okay, which I'm not. I don't think I have some slides on it, but I'm not sure I'll have time to say more about it. But the point is that it can be done, okay. And if you are, you know, like if all this is a lot of jazz, you know, like you can just remember these things, okay, that I put in bold, okay. And what we have done, we kind of separated out these modes, okay, and we have kind of constructed a set of an effective action which describes a very slow fluctuating metric configurations, okay, basically gravitational waves if you want, okay, you know, like which have both the Hawking as well as the quasi-normal modes, okay, and these are linear Einstein configurations which, you know, like if you know what I'm talking about, they are also Schwinger-Keldysh saddle points, okay, which kind of describe the open effective field theory of gravity outside a black hole, okay. The slow modes of the gravity outside the black hole. We can now compute. We have a way of computing their action. We can kind of compute their stress tensors and the kind of questions that Ian was asking. Okay, and we can kind of relate it to kind of, you know, what you expect out of fluctuating hydro. Okay, effective field theory of the fluctuating hydro.
I have a conceptual question.
Yeah.
So usually such actions will depend also on the initial
Huh.
One of the biggest issues there is that you can have off-diagonal, in principle you can have off-diagonal density matrix which are not diagonal in this macroscopic configurations of fluid.
See, as far as the slow modes are concerned, I can deal with any initial conditions. That's the point. The point because I freeze them out. Okay, they are not part of the dynamics. Okay. No, that's the point, right? So see, when it's a question of how you do effective field theory. When you do effective field theory, you take the slow mode to be in some arbitrary configuration. You make some reasonable ansatz for what the fast modes are doing in this configuration, and you integrate them out. Right? That's how you always do effective field theory. Okay. Now, if you give me some very like random initial condition for the fast modes, this effective field theory cannot deal with it, because it's supposed to be a slow mode effective field theory. But a slow mode effective field theory should be able to deal with reasonable initial conditions for the slow modes. Okay, which means that, for example, you can give me any kind of detailed configuration of, let's say, slow part of the Hawking radiation, and this effective field theory will describe how that Hawking radiation will relax. Okay. Yes, in general it does. Yeah, so in general it has a class of initial conditions for which it is valid, okay, where you can give any kind of reasonable initial conditions for the slow modes.
Yeah, and then my second question was that.
But let me just finish that answer. But the fast modes are assumed to be thermal, okay, and they kind of, and that I need to assume to kind of integrate them out. It's like what happens to air molecules. I need to understand. I need to assume the air molecules are all some ideal gas, thermal gas, okay.
Okay, so the second question was that typically in such cases you have some two time scales. One is the time scale like of T inverse, and the other is something like a decoherence time scale. I don't know what is that analogous time scale here, but in such, if you go below such time scales, then the off-diagonal, even for macroscopic configurations of fluids,
Yeah.
there could be off-diagonal configurations, which are the density matrix is not diagonal in this macroscopic fluid.
Yeah, most of the time these things kind of decoy very fast. They are part of the fast modes. It's like asking for a pendulum moving in the air. Okay, what about like pendulum superposition here and here? Okay, those kind of modes decoy very fast. Okay, usually a pendulum coupled to air, okay, becomes classical very quickly. Okay, by the time you are thinking about a classical big pendulum, okay, in that time scale it's just classical. Okay, I think like I'll just let me just finish this, and then we can discuss it more. Okay, so I wanted to say something about the technical details, but maybe for the want of time, I'll probably just skip this. But this is the basic idea. Okay, so there's a way of doing it by reducing all the gravity equations to scalar fields and so on. Okay. I don't think the 2 minutes will be sufficient, but maybe yeah, I'm almost at the end. Okay, so let me just roughly say how this works. Basically, what you need to do is that you have to kind of take the gravity equations. You have to kind of separate it into horizontal modes, vertical modes, and so on. Okay, and what you get is a bunch of scalar fields. Okay, which kind of all have, some of them are fast modes and some of them are slow modes. All of them obey this kind of an equation, okay, with some index m, okay, and the index m determines whether it's a slow mode or a fast mode, okay, and what we see is that, so there's some generalized Klein-Gordon equation with some dilaton which goes like r to the power m, okay, and the m takes various values, okay, for example electromagnetic waves are normally falling, okay. This is in ADS d plus 1, okay, and grazing electromagnetic waves, gravitational waves are normally falling, and so on and so forth. So usually the m is negative gives rise to slow modes, and m is positive gives rise to fast modes. And the fact that we can all describe all of them uniformly is technically it's very good, okay, because we can kind of treat them all uniformly, okay. And the point here is that if you do GKPW boundary condition, okay, which is basically taking into account correlation functions by integrating out all the bulk fields, okay, slow and fast modes, and what it amounts to, this is a question of just writing down the equations and checking it, is that it amounts to the GKPW boundary conditions, which integrates out everything, okay, actually amounts to putting Dirichlet boundary conditions on fast modes and Neumann boundary conditions on slow modes, okay. So what you can do is that you can kind of change the GKPW boundary condition, okay, where you can just for the slow modes, by making it a Dirichlet boundary conditions on all modes, okay, all of the scalar modes. So what that amounts to is not integrating out the slow gravitational degrees of freedom, okay, and then it freezes the slow modes and integrates out the fast modes, okay. So basically what it amounts to is to doing a Legendre transform in the slow modes, okay. So rather than computing a 1 pi effective action, which if you have slow modes is just a horrible thing to do, okay, you compute a Wilsonian effective action where you kind of Legendre transform with respect to the slow modes. So you freeze out the slow modes, integrate out the fast modes, okay, and that you can do by Dirichlet boundary conditions on all the modes, okay. So that's a basic thing. There's some technical details. There's this thing. So let me just summarize. Okay, these are all maybe this also I can skip. There are various kind of things that one can calculate with these things. So let me just go to the summary. So what I have tried to convince you is this thing that like you have that what we can do is that one can kind of integrate out the fast dynamics in the gravitational side, okay, to get like slow Hawking gravitational wave configurations where you have slow Hawking waves and slow infalling waves which are kind of have some effective theory which describing then, okay, and that reduces to a fluctuating hydrodynamics in the dual theory, okay, and the point here is that so there are many future directions which is to kind of how to extend this, okay, taking into account more and more interactions and the non-Gaussianities if you want, like both on the fluid side as well as in the gravitational side, okay, and the point is that there's this question which is also as I said I'm interested in, which is about what is the analogs of these things in the cosmology. So let me just stop here, okay, and thank you. Yeah.
Questions?
Sorry.
Maybe a short question. So suppose if you would take a superfluid or something like something that is in the bulk there are superfluid descriptions, then I'm pretty sure what you'll see is that you will see some decoherence time scale below which you will have off diagonal configurations. So your density matrix will not be diagonal in this even slow modes, right? So how do you deal with that in your formulas?
I think so superfluid we have not done the calculations, okay. It's actually a very interesting question because superfluids have further slow modes which just come from the superfluid order parameter, okay, but yeah, so the point is that decoherence is it depends on the initial conditions, I think, okay, in the sense that like you can start with very coherent initial conditions which I think will take a long time to decohere, okay, as opposed to other thing. I mean just to take in scalar fields, if you just think of scalar fields, scalar field theory has free scalar field theory has two classical limits. It has a classical particle limit and a classical field limit, okay, and the decoherence of these two guys is different, okay, depending on the environment. So it depends on the initial state and depends on what you're talking about. Yeah. So
my question is more about your approach.
yeah. So and this will also do this in a sense that there's a Schwinger-Keldysh effective action, and it will give you different answer depending on what initial conditions you feed into it. That's what I'm trying to say. Yeah.
Okay, we can have one more question, one last question if there is any. Okay, we already had enough questions in the session, so let's thank Rekha for a wonderful talk. Okay, so now we have Felix talking about quantum chaos and effective field theory.
Okay, so thank you very much for organizing this nice meeting and having me here to speak. So I'll tell you about mostly about work that's still in progress with these people. Should come out very soon, I hope. And so the context is kind of similar to what Loga talked about. This is about thermal systems and asking about how they dynamically behave on various timescales, how they relax to equilibrium and explore phase space and so on. And I will focus more on questions about quantum chaos. And what I mean by quantum chaos is, in a sense, it's just a set of various statistical universalities that we can try to understand in a general framework. So we would like to understand what are such universal properties that these systems exhibit. Typically, the systems I have in mind are strongly interacting systems, holographic systems, and also sort of map out what are these universalities and how are they related, what are different characterizations of such chaotic systems, and properties that they display. So let me just say a little bit more about these pictures. So we just heard about hydrodynamics, which is sort of the paradigm for much of what I'll be talking about for an effective field theory that's extremely successful in capturing thermal physics, and specifically the relaxation of conserved quantities to equilibrium. And as we've heard, that this can be described in ADS-CFT in terms of fluctuations of horizons of black holes. Then what I'll be talking about more in this talk is a quantum notion of the butterfly effect. That one simple-minded way to describe it is to just think of some quantum system that I illustrate here in terms of some tensor network or quantum circuit or something. And you can imagine perturbing such a system and following the perturbation through the system. And if the system is sufficiently strongly interacting, perhaps even with all-to-all interactions, like in this picture, then you can imagine that such a perturbation spreads exponentially and sort of affects the system very quickly. And this in ADS-CFT is related to other properties of black holes, of infalling probes or of shock waves near the horizon. And then finally, what I won't have talk about today, but is also closely related, is to ask about the specific details of the actual spectrum of such a system, and what kind of universalities you can discover in such in the spectrum. And it's well known that these are, for chaotic systems, these are described by universality that's described by random matrix theory, but by the eigenvalues of random matrices. And we have learned over the last few years that this in ADS-CFT is related to certain topological features of the spacetimes. Okay, so there's, I gave a few examples of some manifestations of chaos in such systems and how they're related to gravity and to black holes. And the theme of this talk is sort of to try to use effective field theory methods to understand some of these features. And again, the paradigm for that is hydrodynamics, where we understand quite a bit at this point about how to construct an effective field theory in the sense of an effective action and so on. And that's based on symmetries and identifying the right degrees of freedom and so on. And but I won't be talking about hydrodynamics, but mostly about this second point, this quantum butterfly effect, and how to adapt some of these ideas to think about that. So in hydrodynamics, to just one last slide about that, we're interested in correlation functions of conserved quantities, for example, and we understand that the degrees of freedom are basically embedding maps of fluid elements into space-time. We understand that this is an effective field theory in the sense we know what's the small parameter, how we can do a systematic expansion. And some of the obstacles when we try to adapt these ideas to this quantum chaos is that we have to go back to these basics and ask what are the correlation functions we're interested in, what are the effective degrees of freedom, and what even is the small parameter that we expand in. And I'll try to answer some of these questions and develop a bit of formalism for how one can do this. So this is my outline. I'll review a little bit what this quantum butterfly effect is, and some effective field theory way of thinking about it. And then I'll discuss a particular model which is related to the SYK model, where we can understand the case of submaximal chaos, which is quite a bit more subtle than cases with maximal chaos. And I'll say what these words mean in case that's not familiar. And I might have time to talk about a different way of thinking about the butterfly effect and the holographic application, but it's also quite possible that I'll just skip that. Okay, so let me review very briefly. So the classical butterfly effect is this well-known sensitivity to initial conditions. And the quantum butterfly effect is supposed to be a quantum version of that, and we can describe that by thinking about the Hamiltonian time evolution of some operator in a quantum system or in a quantum field theory, and we want to capture the notion that such a time-evolved operator is somehow complicated, even if the original operator was simple. And this should have to do with the fact that doing time evolution corresponds to getting successively more commutators with the Hamiltonian, so the operator somehow becomes much more and more complicated and becomes it grows as an operator in a sense that I might try to make precise later. Okay, so how to quantify that? One way to quantify that is to compare the following two states, let's think about them as states or these two configurations where we insert a perturbation y at time 0 and the second one, or a second operator or measurement at time t, and we compare these two time orderings where the green contours are Schwinger-Keltisch contours that tell you how these operators are inserted in time. And we can quantify how these two states are different by computing their overlap and ask how that depends on time. And clearly for very small times, when t is close to 0, these states should be very similar. And as you can see here, this OTOC correlation function is normalized, is 1 in some normalization. And then as time evolves, this quantum butterfly effect kicks in, and these states sort of become more and more distinguishable. So that's a notion of quantum chaos that I'll be looking at. And one characteristic time scale associated with that would be the scrambling time, which for now I'll define as the time when this out of time autocorrelator differs from 1 by an order 1 amount. And as you know, this quantum Lyapunov exponent is subject to this chaos bound, which is saturated in Einstein gravity, in theories dual to Einstein gravity. Okay. Yeah. Yeah. So exact. So that dot 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 part is what I'll be interested in. I'll refer to that as the Ruel regime, but so this dot 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 part would be higher orders in 1/n, and in particular, when times are of this order, then anything, any term in this dot 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 that has this form 1/n e to the lambda t to any power you want will be a significant contribution that we should keep track of, and you need to keep track of all these contributions if you want to reproduce not just this exponential decay here, but the late time behavior. So this theory that I'll be describing is supposed to capture that. Okay, so I have to review a little bit more how to do this in the case of maximal chaos in some simple example. And then what I'll do after that is sort of a generalization of that, which will hopefully make sense once we're on the same page regarding the maximally chaotic case. Maximal chaos meaning that this bound is saturated. Okay, so you can be more general, especially in that case, but let me describe it in a specific context, which is the SYK model, because it's very simple and we can understand it in a lot of detail. And so the SYK model is this quantum mechanics with random couplings, which we can solve in the large n limit and in the strong coupling limit. And to do that, people introduce a mean field description in terms of these bilocal correlation functions that describe the large n effective behavior of this system. The effective action for these mean field variables that you get exhibits this this reparameterization symmetry, which is broken to SL2R by the saddle point. And this SL2R symmetry sort of plays an important role, seems to play a very important role in all these cases where we have maximal chaos. And what's also quite a universal thing that you can see explicitly in this system is that this strong coupling behavior is described by this Schwarzian effective action, which is the action cost that you get for these reparameterization for generic reparameterizations that are not SL2 transformations preserving the saddle point. And of course, this action also describes the boundary degree of freedom for JT gravity. Now, the role that this Schwarzian action is going to play is that it gives a universal and enhanced contribution to all sorts of quantities, to thermodynamics, for example, but also to these out-of-time order correlation functions that I'll be interested in. So the 1/n contribution here, for example, would be described by the exchange of this Schwarzian mode in the 4-point function. And so let me explain how to see that, how to get that term, for instance. And this is well known. I'm just trying to review this a little bit and then phrase it in a different language. So the way you would see that term is to realize that the 2-point functions of these operators that I have in my 4-point out-of-time order correlator, they couple to this reparameterization in a universal way. It's sort of like a gravitational coupling, by just like a reparameterization of the 2-point function. And this coupling gives us these natural bilocal operators in the theory, and I can then perform a path integral weighted by the Schwarzian action over this Schwarzian time reparameterization mode to get this enhanced contribution to the 4-point function. So you can do that, and the simplest thing you can do is to just linearize the action around the thermal saddle point and just consider these small fluctuations and consider their contribution. So that would be like some kind of tree-level contribution to this 2-point function of these bilocals. And that's all you need. So you can evaluate that explicitly, and it gives you, if you analytically continue this Euclidean calculation to this out-of-time order configuration, then it gives you this exponentially growing piece. Okay. So this is only the first order in 1/n, and I didn't really do a real-time calculation. I just did a Euclidean calculation and then analytically continued the result. So let's try to do a little bit better. And we can do that by considering the Schwarzian action and consider it from the get-go as an action defined on this contour that's appropriate for calculating the out-of-time order correlator. Okay, and I'll use some. So T is going to be the real time that this complex plane refers to, and S is going to be some contour time that just parameterizes the contour. So S runs from 0 to 4t plus beta in this picture. So this will just be a convenient way to write things. And now the point is going to be that when we study fluctuations around this thermal solution, but on this contour configuration, there will be certain modes that live on this contour and that sort of mess up our large n expansion. So this parameter C here is the stand-in for n. That's the large parameter in front of the action. And this large parameter will be sort of cancelled by these soft modes that I'll discuss. So let me sketch it a little bit more, what this is going to look like. So we start from this path integral over this reparameterization mode described by the Schwarzian action. And I'll show that for large t, this integration is dominated by certain modes. You can call them scramblon modes if you want, that are parameterized not by functions of time anymore, but just by some parameters, x plus minus. And the important or the large contribution to this integral comes from the integral just over these parameters. So I'll have to tell you what these parameters are and what's their action, and how do they couple to these to the operators. But the point is going to be that this action is not just proportional to n, but also to e to the minus t. So for large enough t, for t of order log n, the coefficient in front of this action is not large anymore. And then I have to do the integral over these parameters exactly. Yeah, so and that will resum certain 1 over n effects, namely the ones I talked about before, these effects that go like n over e to the t. Okay, so how does this work in this case of the Schwarzian action? We can again consider just the quadratic action of fluctuations, and then observe that this quadratic action now in real time, so there's a minus sign here now, has these soft modes that have to do with the SL2R symmetry of the Schwarzian that go like e to the minus t and e to the t. So these modes depend exponentially on t, which means that I can, even if I excite them very weakly in the past or in the future respectively, they will grow towards the future or the past. So for instance, this plus mode, I can will grow towards the past. At time, if I excite that here, then by the time I get to t equals 0, this mode will have grown to an order 1 amount. And the inter. Sorry. Yeah, that will not be important for this. Yeah.
Typically, if you don't keep all the soft modes, effective approach is always a problem.
So I'll argue that what I'll be capturing are the modes that give the dominant contribution to this integral. Of course, there's other modes here, and if you embed this thing in SYK, there's all kinds of other modes, but I'll be capturing
the part integral, you should always have this extra soft mode, like this on the third one. Just wondering if that doesn't give you some kind of non-local or some bad contribution. You may capture the dominant contribution.
Yeah.
But maybe if you go a little bit subleading, then if you're only interested in the dominant one, you can. So if you just do the saddle point,
Yeah, we'll see what these capture. Yeah. Well, also note that these are maybe a bit different from what you're thinking about, because these modes, they depend on the insertion times of the operators. Okay. Okay, so we can consider the following configuration for turning on these modes. We turn them on according to what you see in this picture here. So the plus mode is turned on these delta functions mean on the segments 2 and 3 of this contour, and 3 and 4 for the other mode. And we can also extend these. So these are infinitesimal SL2 transformations. We can also extend these to finite SL2 transformations. Like this. This would just be the finite version of that, which we need to couple to the. So we don't need that at the level of the action, but we need the finite version at the level of the bilocal operators when we couple to in these 2-point functions. Okay, and now you can just evaluate this action on the contour, on this configuration, and you find this at the quadratic level. You find this action that goes like the large parameter times e to the minus t times x plus x minus. And this is sort of very similar to how they already thought about that in this Maldacena-Stanford-Young paper. Okay, now, yeah, okay. So once you have the action, you can go on and compute the 4-point function with that. And these bilocal operators on the top right there, they just couple to the finite version of the reparametrization that I had on the previous slide. So in other words, they are the 2-point functions of the external operators, fully back-reacted in the presence of these sources. And then you get also a result that's been known, which is some hypergeometric function. So you can just do the integral, and you get some result that depends on e to the t over the large parameter. And if you plot that function, it just looks like this is the graph I had before. So not the dotted line, but the solid line. It knows about these late time effects. Okay, so and you can, yeah, that is still maximal chaos, yeah. And you can.
That's a very, very stupid question. Like that's a complete trivial answer. So you have why do you need a four-folded contribution series? Because suppose you have just simply a usual condition while you're sorting from you go towards the future, it will increase and then it will decrease.
Mm-hmm.
So if you have some non-trivial state, shouldn't that also create some effect?
So it's important that you have both of the modes. And so the action is proportional to x plus x minus. Or so if you only turn on one of them, then sort of not much would happen because of the Schwinger-Keldysh unitarity, basically, that if you don't, if you turn on this red perturbation, but if you don't probe it in the future, it sort of doesn't have any effect. So it's important that you turn both of them on and you probe them in some.
No, but if I don't have a tree-level value of those loop, then it can have some effect. Like this two-point function, the time reparameterization mode can have few effects. And if I have see something like an explicit, because there also we have something like forward, the future directed, one past directed, and you can like keep one on one lane and the other on the other lane, not both on the same lane.
So you want a two-point function just of the w's, for example, or what?
Yeah, say one on the future leg and the other on the something like a g greater or g less.
So that's just a two-point Whiteman function.
Yeah, but
That's not going to have this exponential time dependence.
even if I
And
give a loop contribution, it will probably not.
no. No, so, yeah. So here the way you get this action that's responsible for this, in some sense it really comes from this third piece of this third segment of the contour, where both of the perturbations are turned on and interact.
Okay, so where they overlap.
Yeah.
You need a piece where if you have just two legs, you don't have an overlap.
Yeah.
I see. Okay, thanks a lot.
Okay. So there's also a CFT version of that, but I think I'll just flash that. So it has to do with the fact that in CFTs you also have reparameterizations. Two copies of them, and they're also broken by any state to global conformal transformations. And you can think about an action for these things, which also has similar zero modes that now have a spatial dependence. And in the end, you get some similar hypergeometric function for the out-of-time order correlator. But again, there's some SL2R symmetry and maximal chaos. So this is an identity conformal block contribution to 4-point functions in 2D CFTs. But what I want to ask now is, what about cases with submaximal chaos? And yeah.
So this picture of this x plus x minus over, it also extends to other point.
I think so, yeah. So if I have time, I'll talk a little bit about the 6-point function in the end. We can do something similar, yeah. But it hasn't been worked out in as much detail, especially in this way of doing it. Yeah.
But there also you just have a universal 3-point function and then.
I think the important contributions are still 2-point functions of the Schwarzian guy. Just they're now being exchanged between 3 pairs of operators, for example. Yeah. Okay, so let me discuss now, go away from this case of maximal chaos. And the example I'll discuss is still related to the SYK model, but in this large Q limit. So we consider the SYK Hamiltonian with couplings that have Q indices, and we define the Gaussian average in an appropriate way such that there's a nice large Q limit. And I'll discuss this type of large Q limit where we take large N first, and then we consider the large N effective description and take the large Q limit of that. And you can study that in this G sigma formulation, and you'll find that the leading effects at large Q are described by some nice effective action. So there's an action for little g, that's the large Q fluctuation around the free solution in this collective G variable, and it has this Liouville type action. It's a bilocal action. So this G field is a bilocal variable, and it has a bilocal action in this large Q limit. So we can study this action and try to get from this action this iconal action that I described before, and a description of submaximal chaos. So submaximal chaos because in this large Q limit, the out-of-time autocorrelator grows exponentially in time, but with a coefficient v, where v is some number between 0 and 1 that parameterizes the coupling strength. So in this large Q limit, this 1/n piece of the OTOC is actually known exactly. You can just compute it and get some mess, but it's an exact expression that's valid at any value of the coupling. So it's a nice example where we can have something to reproduce. But of course, we also want to understand these higher order effects in 1/n, and we want to. Neither of these papers I'm citing there uses this effective field theory way of thinking about it, but we want to get something like that from this generalized Keldysh effective action. Okay, so there is some work like that. So there was a paper last year or 2 years ago by Gu, Kitaev, Zhang, where they argued that they studied quite generally theories dominated by ladder diagrams, which includes this large QSYK system, and arguing that in general there's a way to think about these systems or 4-point functions in these systems in terms of such an iconal action. There's also this paper by Stanford, Yang, and Yao, where they studied a formalism that's more similar to what I'm discussing in a system called Brownian SYK, which is an even simpler toy model. And I'll be more following that kind of logic. Okay. Okay, so let's try to mimic what I described before for the Schwarzian theory. And one can just try to do the same thing for this system, where the action we work with is this Liouville action I described. And that turns out to work. It's just more complicated and more subtle. But at the end of the day, it works. So I'll draw pictures like this, where so the variable I have is now this bilocal field. So it depends on 2 contour times. So I sort of have 2 copies of my OTO contour, and I'll draw that in a 2-dimensional picture. Okay, this is the equation of motion associated with that Liouville action, and it has this well-known general solution that's also given in terms of time reparameterizations. And this general solution also happens to have an SL2 symmetry, which is the diagonal SL2R symmetry acting on these F and G reparameterization fields. The saddle point solution is similar to what we had before. It's some tangent of the time variable, but now the V parameter appears. And okay, and we can do the same thing as what I described in case of the Schwarzian, and consider these SL2R transformations, where we just now have to keep track of the fact that we have 2 copies of that we have a bilocal theory. But in any case, we turn on So we do these finite SL2R reparameterizations, as discussed before, that we turn on and off piecewise along the contour. So on contour segment 2 and 3, in one of the time variables, we turn on this plus transformation, and then on 3 and 4, the minus transformation. And we do a similar thing for the G variable. Or in pictures here, the blue and the red regions would be the part of where the bilocal field is, the part of the two copies of the contour where the bilocal field is turned on. And you see that the saddle point solution in general has some constants here that can depend on where you are on the contour. And one of the subtle things that one has to figure out is that these seemingly irrelevant constants can actually be fixed such that these fluctuation fields are consistent with the KMS conditions, despite the fact that you have this V here, which seems to, give you trouble when you try to impose KMS. Okay, how much? 3-0. Oh, okay. Okay, so you can evaluate the quadratic action of fluctuations on these configurations. And I mentioned that before. It was this third segment of the contour where we got an interesting contribution. Now here, the analog of that is the regions where these blue and red configurations overlap. They give you an action, and the action has this form. So it goes like n and e to the minus vt in this case. So the exponential time dependence now has this v inside, which was the parameter for the coupling strength that tells us the Lyapunov exponent has been reduced. The full result you get for the out of time order configuration in this approximation is again some hypergeometric function with the main difference being that the time dependence now goes like e to the vt, and the Lyapunov exponent is correspondingly smaller. Now here's just a comment for people who might have thought about this. Has not much to do with the rest, but just to point this out. If you think about this OTOC, so this hypergeometric function, for the case where delta is the operator dimension, which is 1/q, which is now very small, and this hypergeometric function behaves in a funny way when this delta is very small. So you can see from these pictures here, I'm plotting the OTOC here logarithmically, so you can see that as a function of q, the time it takes for the OTOC to decay by an order 1 amount grows like 1/delta, like q. So this is a much longer time scale than the log n we had before. And in particular, it's a much longer time scale than the scrambling time. If I call the scrambling time the time when the OTOC departs from the exponential behavior. So at very early times, you see this here, that this green line tells you that you have exponential growth that goes like e to the vt. But this doesn't last very long. And when it ends, the OTOC is still extremely close to 0. So somehow this scrambling only lasts for a very short amount of time. And then you have a very, very long Ruel regime, if you like. There's sort of two time scales describing this behavior. So, yeah, that's just an interesting feature about this model. Now, okay. Are there any questions about that part? So I'll say a little bit more about a generalization of that. Yeah.
So the Lyapunov exponent in these large Q models can be setting.
Yeah, so this is V. The Lyapunov exponent is V, which is between 0 and 1.
But is there even if the V's can be set to very close to 0?
It could even be very close to 0. Yeah. That would be the weak coupling regime. Yeah.
And then what happens to these things? What happens to QC?
Well, it would.
So control regime takes a long time to kick in.
I think. Yeah, so this plot is for v equals 0.8. I think you can make v smaller, and qualitatively it should be the same. I think I haven't actually done that, but that you have these two different timescales doesn't really have much to do with v. It's more a feature, a consequence of large Q. Yeah.
Just to understand, so to have this effective physical description, is it going to be true that I would need a bilocal fields, a description in terms of the bilocal fields to begin with? Is that going to be true, or?
Whether you need that or what?
I mean, so far, as far as I can see, that it does depend on that, right? I mean, you need the bilocal fields to have the effective field
in this particular example, yeah.
So away from this example, you would not need that.
Well, yeah. I mean, something that needs to be done is understand other examples, and I think one nice example one should look at is 2D CFTs, where you take into account more than just the identity block. Well, yeah. So it will look different. You know, what I presented here was very specific for that example, but the general idea that you have you have a path integral formulation and a large N description, and then you can study that large N action on this contour and look for soft modes and so on. That should be pretty general.
I see. So
Yeah.
your statement is that as long as I have a bunch of soft modes, I should be able to write down this effective description.
Yeah, yeah, and
At large.
yeah, and I want to discuss a case now that's a bit more generic, where for example, what I'll discuss now does not have an SL2R symmetry, so.
So here you also have the time determined position mode, like you draw it in space. So what I want to ask is that what do you have an intuition of how this V comes from the coupling, or why the V changes? Because the V seems to be dependent purely from the Schwarzian part, right? On power by the Schwarzian part. How is the V changed by?
So V is just a dimensionless version of beta J. It's just a coupling strength.
True, but why does it affect this universal Schwarzian?
Uh,
Because in a large Q, the Q limit also is a Schwarzian action, but maybe there are some other Liouville potentials. If you convert it to a Liouville theory, it will have some other potential, and that potential is responsible for this. The Liouville mode has a different potential in the Schwarzian.
Well, it's I'm not quite sure I understand the question. So
You have a more understanding of this particular example, why you were able to dial this, why does it depend on this particular beta G? If you take this beta G goes to some, if I limit, you get a Schwarzian.
So the idea is you want, away from large Q, everything in SYK still depends on beta J, of course. It's just more complicated, and you have to work hard to get it order by order. The point is that in the large Q limit, the beta J becomes a parameter that you can that just goes along for the ride, and you can solve it.
So this SL2 symmetry is broken like this.
So this Liouville theory, you might think, has two copies of diff S1 symmetry, and that is broken by the saddle point to one copy of SL2R. That SL2R, I believe it doesn't play much of a role. It's more of an accident, I think. And in what I discuss next, there is no SL2R. The fact that there were still reparameterizations is, we kind of use it here we use these reparameterizations to sort of generate the solution, to write the saddle point in a simple way. but again, they don't seem to be the crucial thing. And in fact, they're absent in this case. Yeah, I think the large Q SYK just has some of these features that it inherits somehow, and that perhaps obscure a little bit what's important and what's not. And
There is no way of doing something like about conformal coordination.
conform.
Away from this, this limit that this bigger vector.
Yeah, you can also do that. Well, that's what one usually does in SYK for small q. That when you want to understand the corrections to maximal chaos, you have to do something like that. But that's sort of in this large Q limit that's already packaged into the V parameter. Okay, so a few comments about a chain of large Q models. So I have now large Q models, and I couple them in a chain, where the chain couplings are nearest neighbor couplings, and they also have a large number of indices. And that system also has an effective description in terms of some Liouville type theories that are now coupled. So there's some coupling term between the bilocal fields on site X and site X plus 1. The saddle point solution to these is homogeneous in X, but then the fluctuations are not. And you can again do what I just talked about. I will not go through it again, but you can follow the same procedure and derive an iconal action for this model. And it looks kind of like what we had before, but there's now a momentum integral. So there's now spatial dependence, or an integral over momentum, and these x plus and x minus parameters of these modes that I discussed depend on momentum. And consequence of that is that when you compute the OTOC, let's for simplicity just talk about the 1 over n piece, then you have to do a momentum integral, and so some Fourier transform to get the spatial dependence. And this Fourier transform is kind of interesting. So it has a term in the exponent that goes like h of k minus 1. So h of k is some parameter that tells you about the momentum of the fluctuations in this chain. It's such that for 0 momentum, h is 2. So in that case, this prefactor would be 1, and you get the v times t dependence in the exponent. But more generally, you get some momentum dependence in the exponent. And then this Fourier transform also has a denominator that depends on k and has some poles that play an interesting role. And there's explicit expressions for that. I'm just sketching what it looks like. But the point is then that, and this is quite general, this is the same structure that appears more generally, and specifically when you consider stringy corrections to the gravity iconal phase that were studied in this paper, you get the same type of integral. So this integral encodes an interesting mechanism. And the mechanism roughly goes as follows, that how you evaluate this momentum integral depends on whether x in units of t is large or small. When x is small, then the dominant contribution to this integral comes from a saddle point in this exponent. And the saddle point gives you some contribution that goes like e to the vt again, and then some damping in space. And for large x, the dominant contribution to this integral comes from a pole in this denominator. And this pole gives you a contribution that takes this form. So, okay, I'm not going into the details, but the point is that the mechanism here is more subtle once you have a spatial dimension, and then this model actually exhibits the kind of thing you would like to see when comparing with these stringy calculations in gravity. Which in gravity, these string scattering corrections are the thing that changes the Lyapunov exponent. Okay, so I guess I still have some time to do this, or should I stop and do questions? Okay, so then let me briefly describe. Okay, so let me briefly discuss it a slightly different way to think about this butterfly effect. So more practically, if you think about this SYK Hamiltonian, you can think about the spread of some perturbation through the system, and because of the all-to-all interaction that happens exponentially fast, like this. And you can try to quantify that, and you can ask what's the size of this perturbation as a function of time. And it will grow, initially it will grow exponentially, and then once a sizable fraction of the system has been infected, then it will, the growth will slow down and the thing will stop at some point. And at least in this simple system, there's a way you can make this precise to quantify the size of this perturbation. So to do that, you introduce some bases of operators you have, which are just strings of fermions, and you canonically purify the system. So you introduce a left and a right copy, and that allows you to write these operators. To write let's call it a qubit basis for these operators, which are of this form that they involve a left and a right fermion. And in terms of these, we can define a maximally entangled state as the state that's annihilated by all these qubit operators. And we can represent that in pictures as a bunch of lines, which are sort of these different states. Or the maximally entangled state will be represented as this collection of shared qubits between the left and the right system. And then when you act on that state with a dagger of these operators, you create some excitations, and you can ask what's the size of that perturbation. And the way to compute that is to define some operator that was written down here. And I'll call that the size operator in this context, which is just a collection of all C dagger C. So that operator counts how many of these operators have acted on this shared maximally entangled state, or it counts the numbers of flavors contained in some operator. So if I compute the expectation value of this size operator in some operator, that's some string of fermions, it's going to return the number of flavors contained in that. And I can now take this picture I had, this collection of qubits, and I can perform operations on it and construct a quantum circuit out of it, meaning that in every time step, I act with some random unitary operators that, for example, act on pairs of qubits, and then I reshuffle the qubits, and I do the same thing again. And I build a circuit by acting on these qubits that way. And then, of course, again, what I just had, if you act with some perturbation, then in this time, as you time evolve this circuit, as you put down more and more gates, this perturbation will spread exponentially. And in fact, such circuits or similar circuits have been proposed in the context, in this discussion of circuits and tensor networks as a model of black hole time evolution. So in particular, it's been argued that such a circuit represents the evolution of the black hole interior in some coarse-grained sense. So it gives you some kind of coarse-grained representation of the interior geometry. Okay, and in that picture in some sense is like a circuit version of the Schwinger-Keldysh contour. So if I put some perturbation in the circuit here that spreads towards in one direction of that circuit and affects the gates there, that's kind of like putting down the circuit in this way. So the circuit also has a notion of left and right time evolution going in the two different directions, and they describe the left and the right of this thermophile double context. And this perturbation on the right would correspond to a shock wave or some perturbation you insert here that creates a shock wave. And the shock wave has the effect that some part of the interior is only accessible to the right. So there's some part of the interior geometry which you cannot access from the left CFT, That corresponds to the fact that some of these gates in the circuit have been perturbed in a way that can only be accessed or undone, if you want, by the right system. Okay, so this is like sort of the quantum circuit picture. In terms of the thermal field double state, what we're doing is, so we're considering this thermal field double, which is like the thermal version of a maximally entangled state. And we consider this size operator that I mentioned. So we consider the size of some perturbation in that thermal state. So does that make sense? I think I'm going pretty fast. But what I described before for this infinite temperature SYK model, we're gonna try to mimic that now in a thermal state. So you can just generalize this notion of operator size to the TFD, and you can evaluate it, and you'll find that the size of some perturbation in this thermal state is actually computed by the out of time order correlator. So that's just an explicit definition that follows from the definition of that size operator, that this OTOC, or the sum over all OTOCs with all the basic fermion operators, computes for you the size. And if you plot that, you get this thing that we've seen a few times now, that we can interpret now as saying that this curve computes 1 minus the size of the perturbation as a function of time, so how the perturbation grows. Or in the language of this quantum circuit, it counts the fraction of qubits that have not been perturbed by this growing epidemic. Now, if you think in terms of such a growing epidemic that spreads to some circuit, you can of course compute the fraction of unperturbed qubits. It's very simple. It's just some epidemic growth that just follows some logistic equation. And you can compare that, and it matches very well with this more sophisticated calculation of the OTOC using this iconal approach. Okay, so you can also ask, if you have two perturbations, just to mention, to get back to what Loga asked before, you can have two perturbations, one from the left and one from the right, and ask about the features of that state. And in gravity, these two perturbations will have the potential to collide behind the horizon. And you can ask what happens if you send them in very early, such that they get highly boosted and there's a very energetic, high energy collision with strong back reaction. What does that do to the interior? And because this operator size, or this circuit model, is supposed to give you a rough description of the interior, it should shed some light on that question. So you can think about this circuit with two perturbations and ask, how do they overlap depending on the time when I insert them, and how many of these qubits get infected as a function of time. And so you can think about that, but if you want to compute a correlation function, you do again the same thing as for the single perturbation. So you consider some state that's constructed by taking the TFD and perturbing it with two operators, one on the right and one on the left. And then you compute the size of that perturbation. So that means you compute the expectation value of our size operator in this doubly perturbed state. And that's an example for a higher point function that's out of time order. And then you can go and compute that. And you find some result using similar formalism. So you have your iconal action that I described, but now you have 6 operator insertions, and you can use similar techniques to compute that, and you find something that looks, it looks a bit similar to what we had before, but this is now for the 6-point function. And it has this gravitational interpretation that the features of this 6-point function, or of the size of this perturbation, tells you about the features of the interior. So when this is close to 0, there's a very weak collision. And as you bring these operators to further down in the Penrose diagram, you get a very strong collision, which corresponds to this regime here. And another way to say the fact that this goes to 1 is to say that the fraction of perturbed gates goes to 1, meaning to all of them. Or in other words, the interior has disappeared almost. So somehow when you have this very high energy collision, there's not much space-time left into the future of that collision. But the singularity comes very close to the shock waves, and all the interior between the shock and the singularity sort of disappears. So we have learned something interesting about the properties of the singularity when you have this highly boosted collision. Okay, so I'll stop here. So I have here are some future questions. So you can ask some of these questions in CFTs. I think that would be interesting in 2D CFTs, and then you can also think about higher dimensional CFTs. And in these very controlled models like the large Q SYK chain, there are interesting questions one can ask about the properties of the butterfly front, for example. Like how does it behave, the spatial dependence of the of this butterfly effect. And then there are some conceptual questions about the role of SL2R. Okay, thank you.
Okay, thank you, Felix. Questions?
Does this, is it correct that at very late times the OTOC becomes exponentially small?
Yeah.
So it starts at 1, order 1, I guess, and it decays. And then does it become exponential, like the plateau behavior at very late times, is it exponentially small?
Right, so if you want to understand in detail the very late time behavior, yeah, that's a question one can also think about in terms of these integrals, and that was done, for example, in this paper I cited by Douglas and Jembin.
Right. I was just wondering whether these effects, like the ones that you described for the Ruel regime and so on, they change the time scale at which the value becomes exponentially small.
Oh, for the large Q case?
Yeah. Oh yeah. Right.
I think so. Yeah.
Okay. So what do you have any expectation for? Is it like for times of order e to the n that?
Oh. Probably. Yeah.
Okay.
But I haven't checked.
Okay. I mean, without the Ruel regime, you would have naively guessed that it's much quicker, I guess.
So you always have this Ruel regime, which is the power law approach to 1 or 0. My point when I had this picture was just that this Ruel regime is stretched, it's extended in large Q.
I see.
As opposed to the small Q
Got it.
case that's you often discussed. Yeah.
Okay, thank you.
Sorry, very quickly, I probably missed this. So the size of the number operator that you defined, should I understand that as really the size of the particular operator in the operator Hilbert space?
Yeah, so I only defined it in SYK.
Yeah,
where it is quite literally the number of fermion flavors you have in some operator.
Yeah.
And I think it's an interesting question how to define it more generally. And it's a question that has not really been answered. So there's been some progress in some more general formalism. But
I mean, in general, there is no reason to expect that the operator growth in the operator Hilbert space would be related to an OTOC, right?
Well, I think there are some hints that there are relations. So, for instance, people study something called Krylov complexity that makes this much more precise, the notion in which this grows. And I think there are idea is that this Krylov complexity, so for some time grows exponentially, and that exponential growth is actually related to the growth of the OTOC, at least in certain examples.
Okay, thanks.
Yeah, that's one way to approach this question and make it more precise. Yeah.
So one more question is, if you in the model with this spatial chain model, can you make the spatial couplings also random? And study this?
I did have them random, yes.
You had a randomness in spatial coupling.
Yeah, the spatial couplings were random, also with Q indices, and also from a Gaussian distribution.
Did you have some additional modes, like soft modes emerging because of that? Other than the time reparametrization mode,
I think not, but I'm not completely sure. So one should, I think one has to study in carefully what other modes there are and if they play a role in that case. Yeah.
Any more questions? Okay, if not, let's thank Felix once again. And we will meet in 20 minutes because we are running behind the time.
Okay, yeah, but I'll keep forgetting. I'm sure that I'll keep forgetting it.
Okay, so we have Chethan for the last talk of the session. So
Thank you.
Talk about fuzzballs and random matrices.
Yeah, so let me start by thanking the organizers for inviting me here. So I'll right. So I was my collaborator Arnab is in the audience, and he insisted that I should talk about it. So I was planning to talk about something else, but we'll do it anyway. So please feel free to ask questions.
And he will answer.
I don't know whether he will answer or not. That we will have to see. So anyway, so the idea here is that so what I'll start with is I'll start talking about some background for why fuzzballs may be an interesting idea, because I do realize that fuzzballs are kind of a polarizing idea, which kind of I think the community is sort of split about what the status of the subject. And so in the end, I will kind of present some pros and cons, and you can decide to what extent what we are doing can be viewed as evidence for fuzzballs or not. So I'll tell you what the concrete calculation is and what the result is, and from there, I'll leave you to interpret it on your own. Okay, so let me start by giving some broad background on black holes and fuzzballs and so on. And there are many people in the audience who might be more familiar with the details of some fuzzball stuff than I am, but I think if there are any corrections, please let me know. Okay, so the first point is that the black hole horizon has always been a question of, is a puzzling place, and it has always been the case, but it has recently gotten revived in its interest thanks to these the information paradox getting revamped in the arguments of Mathur and Amps, and especially reviving some of the arguments of Page. So today we will view this as a question. So my goal would be to kind of see what that means for statements about black hole microstates in, let's say, string theory. Okay, so this is the setting. And these, so the fuzzballs are classical solutions. The way it is usually characterized is fuzzballs are classical solutions of supergravity, which are regular, and they are considered to be candidate microstate solutions that cap off before the horizon in some suitable sense and are completely regular. Okay, so this is the defining sort of feature of these solutions, and they provide the foundation for the fuzzball program. Okay, so I'll start by saying what I find interesting about the fuzzball solutions, and the first fact is that it is non-trivial that these solutions exist. And so the point is, in some sense, that a throat that caps off before the horizon, the fact that it exists is surprising in let's say semi-classical gravity, or supergravity or general relativity. So it really requires the sources in general relativity in order for them to exist, and that's one interesting fact about them. And the second and often not so emphasized fact in some sense is I feel that at least some of these solutions are really black hole mimickers, in the sense that the structure is really sitting deep inside the throat. Okay, so which means that far away from them they really do look like black holes, which means that it is, if you want to, you cannot just blow them off as like something like, oh, okay, some star-like or neutron star-like solutions in general relativity. I mean, in the context of quantum gravity, you can't do that. So, or at least I don't think you can do that. So, and the third interesting fact is that there are whole moduli spaces of these solutions. Oftentimes, they're not sufficient to capture all the entropy of the black hole, but at least it is interesting that such solutions do exist. And I will say more about how many of these solutions exist and what are the expectations about how many of them can possibly be found, etc., in various cases. So in the two charge case, when there is in the D1 D5 black hole, it is known that this can geometrically be quantized, the space of these solutions, and you find that the entropy matches, and the scaling with the charges was found by Ryzhkov, and the precise numerical coefficient can also be matched, and this is just follows straight from the calculation. Okay, but the two charge first ball is not a particularly interesting one, so I should put that caveat there, because the horizon is zero size if you don't include higher derivative corrections. So if without alpha prime corrections, these solutions do not have so you might say that, okay, so at the tree level it's kind of a trivial black hole. Okay. So but so let me just correct that, tree level, but I meant is without alpha prime corrections. That's what I meant. Okay, but anyway, go ahead. Sorry.
Yeah, well, which case did you do? Because
K3. K3. So not the T4.
case, I think the exponential number missing.
What is that, sorry?
I think exponential number is still missing. Even
Exponential.
exponential number, so the coefficient is not.
No, that's precisely the one we fixed. So in fact,
I mean, we've shown 15 years ago the exponential number missing.
yeah, I know, but I did it 7 years ago, and I actually no, you're talking. So there is, in the T4 case there is a difficulty, and I can tell you what the difficulty is, because there are fermionic fluctuations which are hard to handle. But for K3, it is actually fairly easy. I mean, you can. In fact, I have sent you the draft, and you liked the paper also. I remember it, but but we can discuss it. Yeah. So, anyways, yeah. So, but K3, it's So in the T4 is more complicated, because there is an issue of fermionic fluctuations which people have not been able to handle. But again, it's largely because of technical difficulty. So I think in the T4 case also, if one is powerful enough, I expect that it can be matched.
I don't think it's a technical issue. The fact that
In the
the ones that are missing, you can understand why they're missing using AKCFT. They're not visible
In the T4 case, I don't want to make a strong statement, but in the K3 case, I would disagree with you. So I mean, we can. Yeah. So right. So okay. So but there are also flies in the ointment. So even beyond this, and the first thing is that so these solutions are only known for microstate solutions are only known for BPS black holes, and which are at zero temperature. So this is one problem, and so that's clearly a problem, because we will generally be interested in cases when the temperature is finite, at least for understanding things like information paradox. And obvious criticism regarding the supergravity microstates, because they are supergravity, tree level, etc., is that the more complicated profile functions, obviously they will have large curvature and so on. So one has to worry about whether any of them are really acceptable. So my feeling is that the first ball community's attitude, maybe I can be corrected on this, is that because these are BPS protected solutions, the fact that they exist may be sufficient even to trust them, or even to believe that some form of these kinds of solutions may even exist in the full theory. Okay, so but at least at the classical supergravity level, these profile functions, they can have high curvature if you just not.
They do, right? It's not only that they can, they do.
Yeah, absolutely. Yeah. Yes, I agree. I do not disagree.
But I mean, I think that the view you put there is a limited view from a very small part of the physical community.
I agree. There are flies in the ointment. That's what this is. So I agree. So my only point is that, if you are computing these, and if for instance these entropies are supposed to be matched with that of the black hole, then I would imagine that the hope is that at some level, I mean, why are people constructing these whole class of solutions if a priori they are failures? And I think that the reason ultimately has to come from the fact that because these are BPS solutions, maybe it is meaningful to construct the solution spaces of them in the hope that, you know, one may find it interesting for this thing. But I also want to say that I'm not a particularly strong fuzzball defender. So, you know, I just wanted to put it out there, unless you will see that there are issues of various kinds that I'll talk about.
There are also non-BPS. There are classes of BPS.
Yeah, but I mean, in that case, I mean, the arguments for their stability, etc., can all be, you know, you're talking about J-Mart fuzzballs and stuff?
J-Mart,
Yeah. Yeah, so I want to stay as, you know.
I mean, in this case, the instabilities are also distributed because they're related to Hawking radiation, but they're very specific.
Right.
States that they represent, and then you can compute what is the analog of Hawking radiation on those, and that precisely matches.
Okay, I mean, so that
It's a smart class rather than
yeah, so that would be a pro argument in some sense. Yeah, so what I'm talking about, yeah, here I'm trying to emphasize the sort of the counter arguments, let's say. All right, so yeah, so then, you know, these are somewhat other technical arguments against them. So Sen has an interesting argument for why, you know, fuzzball's microstate entropy should actually be added to that of the black hole. But there are some counter arguments in some other duality frames from Mathur and Turton. So all of these are somewhat tangential to what I'm going to say. But I'll just put them there because it's a list of these, you know, cons, so to speak. And the final thing, so not the final thing, and the second last thing is that these solution spaces that have been identified in the case of finite horizon black holes, the D1, D5P, the 3 charge black holes, they happen to be only contain a subleading fraction of the entropy. Okay, so and there are, again, I mean, very recent papers. I don't know, I haven't really looked up in the detail, but so there are new solutions they are finding every day, so maybe it can be filled or not. But let's, yeah. So, and I think somehow the most, you know, most basic criticism, let's say, of fuzzballs is that, of course, the things stop at the horizon. Then how are you going to get things like temperature or Hawking radiation or any of these things from a calculation? These things are easy to see when the horizon is smooth. And in fact, I mean, it's very difficult to see if the horizon gets truncated at the, you know, the geometry gets truncated at the horizon. So that's in some sense the most fundamental problem. Okay, so and so yeah, these two are kind of the same problem in a way, because the second one is understanding various aspects of horizon physics in a dynamical setting. Why, and in some, you know, if the claim is that black holes are an ensemble of these microstates, then it's clearly an outstanding challenge to understand how you would see, say, for instance, smooth infall from this. So this is the primary. This is, I would say, the primary problem with the fuzzball paradigm. In fact, this is what solves the information paradox in fuzzballs. So clearly, because fuzzballs are engineered to solve the information paradox, this is the price that you pay. Okay, so the converse, there is another approach to black holes in the community, within quotes, and that I would call, for a lack of a better name, semi-classical approach. It is somehow, you know, it's more, I would say it is probably more, you know, there is broader or at least support from more important people for this. So that means that it doesn't have a real name. It's somehow, you know, congealed in the community's ideology itself. So I will say call it semi-classical approach. Okay, and it draws inspiration from semi-classical gravity and entanglement entropy. Those are, I would say, the two, you know, main things. I mean, maybe toy models of 2D gravity, etc., etc. So that's where it sort of draws its energy from. And there are very interesting results from that. One of them is this idea of maximal chaos and scrambling and hints of random matrix at the horizon that we have seen already. For instance, there are many talks even today on this sort of thing. And probably the sort of the biggest success of this approach in the recent past has been the reproduction of the page curve by using ideas from quantum extremal surfaces and so on. And it's able to reproduce the page curve. Okay, so with some caveats, but nonetheless, it is an interesting fact. I think the most interesting fact about this calculation is the fact that quantum extremal surfaces were introduced for other reasons before this calculation came up. Okay, I think so if you did the calculation somehow, you know, you were introduced this construction as a reason for doing the calculation, then there are problems with the calculation which may make it somewhat shaky, I would say. But if the quantum extrema surfaces are introduced for other reasons, and that's a good, and the fact that they were applied then to do this calculation to reproduce the page curve, it's kind of like Weinberg's prediction of cosmological constant. If we predicted it after we discovered, it would not be anything. But this is an interesting fact. So, and that's one. So this is definitely a very interesting set of ideas that happen here. And I think first of all, people oftentimes ignore this. I think at their own peril. So anyway, so coming back. Yeah, so there are challenges to both of these. So as as Kostas was saying, there are many, and I listed, there are many problems with the first ball proposal, and but there are problems with this paradigm. For instance, I mean, there are many of you are familiar with this. So the final page curve in the island paradigm is compatible with unitarity, but the detailed emergence of unitarity at each epoch of Hawking radiation is unclear. At least that's what I would say. And has raised numerous questions about related to ensemble averaging and factorization and all that. And essentially, I think all of this boils down to the fact that it is some sort of a Euclidean calculation masquerading as a Lorentzian calculation. Anywho, so there is evidence that the semi-classical gravity should be viewed as an ergodic proxy for a time average. Maybe that's the way one should look at it. So the second bullet point is sort of quasi-speculative, but there is some various pieces of evidence which I think is reasonable about that. So, but nonetheless, the point that I want to extract from these things is that it is definitely there are problems that we do not understand in the context of the semi-classical approach, so to speak. So, and in both of these things, I would say that the smoothness of the horizon is still a big puzzle. Okay, so and that's where we are. So this is sort of my two-slide summary of the status quo, and the 4 or 5 slide summary of first balls went before that. Okay. So what do we go to take away from this? Okay, so a natural goal is what is one to make of the situation, right? Perhaps a synthesis of both approaches is necessary, and it's not clear how to make the synthesis because the approaches are completely different, and not simply because we wish to be reconciliatory. I also want to say that because we don't want to just be saying that both are fine, So we want to say that because both camps, I certainly believe, have had interesting results. And for instance, I think, even if you forget about everything else, I think the fact that the solutions these people have been able to find in the context of supergravity, I think it's an interesting fact. I mean, because these solutions, at least they don't naturally exist in general relativity. So they definitely have had interesting results, and they keep finding more. So, I mean, it requires some form of explanation is what I feel. And arguably successes, because I put arguably and certainly here because interesting results both camps have had, I feel. But the successes, they're all kind of somewhat fishy. So, but they are probably successes. So, and they both have like profound challenges that they have to deal with, and that's where we are. Okay. So the question is, how might one go try to synthesize these 2 points of view? We don't know. I mean, so that's sort of the big kind of elephant in the room. And I said this word, how to synthesize this, but I don't have, like how are we going to do that is a real pragmatic question. It's not very clear. So, my talk today that was kind of an extended introduction, and my talk today is kind of roughly in the context of that. Okay, so can one reproduce a success of one approach using the tools of the other? So this is the way I would ask this question. Okay, and we will take a step in this direction. Was there a question? Sorry, no. Okay, specifically, so the thing that I would like to kind of address today is because, as I mentioned, in the semi-classical approach, there are many hints that black holes create. Black holes are responsible for, black holes are maximally chaotic. They have hints of random matrices. There are various pieces of evidence for that. That is one of the, I would say they're one of the interesting results that have come out of this semi-classical approach. And so can we try to reproduce that using this first ball inspired philosophy, let's say. So and can we reproduce, so for instance, very concretely, can we reproduce the level spacing distribution? I'll show you level spacing distributions of random matrices in a bit. And there is a very specific shape that it takes, and also the spectral form factor. So these are two diagnostics of random matrix behavior in Hamiltonians. If Hamiltonians, which are chaotic, mixing, etc., they have there are diagnostics of them that one can identify, and so the question is, can we reproduce those expectations of semi-classical arguments by starting from some sort of first ball inspired starting point? This is our question. So the spectral form factor, so the level spacing distribution, maybe some of you are familiar. I mean, okay, I guess the spectral form factor is also quite familiar, you know. So it's supposed to be a random matrix diagnostic, and if the spectrum exhibits Revel repulsion, it is expected to show a linear ramp. Okay, so this is I'll state it as a fact. We will add some wrinkles to that statement eventually, but right now this is sort of an expectation that is widely held. Okay, so I'm just showing you, flashing you the definition of the spectral form factor for a given quantum mechanical system. You know, you define all these things, and I'm sure you have seen this already in this conference multiple times. So, so we have this sum over the eigenvalues and a complexification of the beta, and that's what we have. So this is our spectral form factor. Okay, so and I'm just showing you a picture of the spectral form factor that I just Googled and found from Google. And so the key point that we are interested in is the part that I'm calling the ramp. So and the important point is that the ramp exists, and it is crucial that it is also linear. Okay, so if you have a ramp, there are sometimes you find ramp-like structures, but as far as I know, there is not a single example of a linear ramp. Linear means in a log-log plot, which means the spectral form factor behaves like is proportional to t. Okay, not some power of t or something. And that linear ramp is generally only seen in systems which also have level repulsion, or in other words, random matrix-like behavior. So that's supposed to be an indicator of strong chaos in some sense. So that linearity of it's not just the ramp that is important, it's the linearity of the ramp is also important. So you can get ramps which are looking weird not weird, I mean, you know, which have other properties in other ways. Okay, so this is so the ramp will be sort of our focus, and the Plato is easy to arrange in a fuzzball situation. For the Plato, it just means that the spectrum is, you know, if you put a cutoff, the spectrum is basically going to be, discrete, and then you're kind of guaranteed to find a Plato. So Plato, the Plato is the immediate payoff that you get, the devil's payoff that you get for sacrificing a smooth horizon. It's literally that. So the question is whether by doing that we are actually going to get the ramp as well. So that's the question. Okay, so anyway, so the expectation is that fuzzballs cannot do this linear ramp because the spectrum of normal modes of a cap geometry is roughly evenly spaced. Okay, so I mean, I don't know whether there is a statement very specifically about this level spacing of random matrix stuff in the literature, but there are multiple places on YouTube, in conferences, etc., that you can hear this. So if you want, I can send you links. So I've not explicitly seen this statement in a paper, but it's definitely part of the zeitgeist. Anyway, so in other words, we expect that the level spacing distribution without repulsion and a spectral form factor without a linear ramp. So this is what naively what one would expect from a fuzzball microstate. Okay, if you just compute the spectrum of normal modes of a capped geometry, this is what you would expect. So so explicit fuzzball geometries, you know, so there are a couple of things to be said here. So if you want to look at a genuinely a profile with a lot of kings or whatever, it's geometries, they are inaccessible at finite. So the multiple reasons why this is a calculation that is only heuristic. You know what I'm saying? It cannot be. Yeah, sorry.
So I have a question.
Sure.
I thought you need to do some averaging over different fuzzball solutions.
Yeah. So.
So what you should be comparing should be some average.
Yeah. So I mean, if you believe that a black hole, so there is a question of difference between whether you are able to distinguish between a microstate of a black hole and whether the black hole is living in a microstate, right? So I think the question in some sense would be like if you are sending a probe or something in, and the black hole, I think if you believe in, generally speaking, that I don't believe that a true ensemble average exists in nature. You know what I'm saying? If that is what you are kind of getting to, I don't believe that a true ensemble.
Can you put the previous slide?
Yes.
I think the puzzle will be more like the red lines.
Yeah, exactly. So that's what we are trying to reproduce. That's right. But I'm just saying that by a ramp, I mean a ramp with these fluxes.
If you in a sense do the computation in a large number of puzzles and an average, you would see the ramp.
Right. But what I would like to see is I would like to see the thing with the fluctuations in a single geometry. That's what I would like to see. So of course, if you have many of them, I can do the average and get the ramp. But I think, yeah, that I can certainly do. But I'm saying that, really in a true quantum gravity calculation, what you would see if you did it for a single microstate is the thing with the ramp and with these fluctuations on top of them, right? So because that's what you would really expect because it's a single microstate.
Yeah, typically this
I agree.
It would be large.
Yeah, that's why it is difficult.
Like they are over there, kind of like the red curves.
Right, I agree.
Fluctuations, but on average,
I agree. I agree with all of that. Yes. So, so that's why it is difficult. Yes. So, but by a ramp, what I mean is, if for a single microstate, what I mean is the thing with the fluctuation. So, to answer your question, like if you really want to see a straight line, you would have to average it. Yes. But the real challenge in some sense of quantum gravity would be to actually reproduce that thing with the fluctuations. So, yes.
What are the features of the spectrum that are necessary and sufficient to be somewhere?
Nobody knows, I think. I don't think necessary and sufficient. I don't think anybody knows. We have some sufficiency statements in some cases, and I think that these are, so that's the kind of thing that I'm trying to get to. Yes. So yeah. So if you, I think a necessary condition. Exactly. Exactly. Yeah. It's a single random matrix. So. For any random matrix, if you just randomly pick a matrix from some ensemble and compute its spectral form factor, you will find the ramp, the linear ramp. But the converse, if you see a linear ramp, whether you are necessarily in a random matrix thing, I would claim that it doesn't have to be.
No, then I asked this question also because if you take a typical state, right, you cannot distinguish it from microcanonical ensemble if your Hilbert space dimension is not. So
Sure.
But if this feature depends on like very details of the spectrum, then you
It doesn't.
expect
Yeah.
typical state to actually.
Yeah. No, I mean, yeah. Then I think that is, if you have to fine tune the answer in some way, then it's not interesting. Yeah, I agree. Okay. So in other words, we expect. Yeah. So this is what I was just saying. That. Yeah. So if the naive expectation from first balls is that you would see a level spacing distribution without repulsion and a form factor without linear ramp. So, right, so explicit first ball geometries are, explicit first ball geometries, what I mean here is the thing with a lot of curvature or a lot of, the profile function being generic. In that case, they are inaccessible at finite temperature horizons. And yeah, so I mean, finite temperature, first ball solutions, I mean, except for these J-Mart cases that Kostas was talking about, in general, we don't have access to them. And for a generic profile, the wave functions in these, wave equations in these things are difficult to solve anyway. So there's a pragmatic and a conceptual problem because most of the solutions are BPS. And even if you are able to solve the wave equations in that case, in that sense, it's not that interesting. But if you are at finite temperature, then you don't have these solutions. And you don't have these explicit first ball microstate constructions. And then you are kind of at a loss to do what is the question. Yeah.
So when we say that this is integrable,
Uh-huh.
the differences that we're talking about are 1/n corrections, right?
Integrable, right? Yeah. I see the question is in the case of first ball. That's a good question because I think that in the case of first balls, so if you are putting a cutoff at Planck scale, so one of the things that I suspect is that the level spacing actually becomes exponential in minus a.
No, but even
Yeah.
it's one thing to solve a wave equation in probe level.
Yeah.
Need some background.
Yeah. Then I think it will be 1/n. Yes. Yes.
But the point is that if you also take into account back reaction, all these things get shifted slightly.
But I don't think they will get shifted by substantially. Yeah. I would expect that they are 1/n type of thing. Yeah.
But isn't there the kind of difference that will get picked up when we come to the ramp and so on?
So I mean, you can see the thing is the calculation that we will do will not be a fully back reacted calculation. So I mean, but the calculation I'm going to do is completely trivial. It's almost like an anticlimax. So and then you can see whether how you want to maybe it is better to ask this question at the end. So yeah, but I think I do agree that it's an interesting question. So
But usually in the random matrix theory, my understanding was that these things happen from finite NFX,
Right. I mean, yeah, because they are explicitly n by n. Everything is you just directly solve them. So it's completely non-perturbative anyway. Yeah.
As n goes to infinity, in some sense the ramp gets delayed.
Yeah, that's true. Yeah. So this is So yeah, I agree. So because I mean, in some sense, it will just die off. You will never see the rise back to the plateau. Yes. So so this is all finite NFX. So but finite NFX in this picture, I think if the first ball picture has to somehow hold up in some way, it will have to involve some kind of truncation right at the horizon. So I think you can ask this question, even though I don't think I'll fully answer it even at the end, but you can, maybe, yeah. So yes, so so the question that we are after is, where am I? Right. So if you really want these BPS supergravity solutions in order to do these calculations, then of course this is not really a very viable thing to do, because as I said, one is it's at 0 temperature, second for generic first balls, the wave equation is not really solvable. But on the other hand, one thing we can hope to understand is that the questions that we are trying to answer are expected to be generic and robust. So which means that maybe if you can, by some luck, if you can just guess the structure that is giving rise to it, then maybe we can, if you do something right, and if it is robust enough in your calculations, then you can take that to be some indicator of something interesting. Okay, so right, so the features we are looking for are expected to be generic and robust, and so features of black holes at microstates at finite temperature, and the ramp and this level repulsion, all of these things are semi-qualitative features which one might reasonably hope to reproduce by doing some sort of a heuristic or inspired calculation rather than fully solving a BPS or fully solving a quantum first ball geometry, whatever that means. So one thing I also want to emphasize, and this is very critical of the first ball community, unfortunately, which is that they don't have any real statement, as far as I am concerned, for the quantum first balls. So all the statements are about these classical. So maybe you can make the statement. I would like to know, what is there a statement, because as far as I know, yeah, go ahead.
I mean, it should be a string theory configuration, but the only requirement is regular, it doesn't have a horizon. And it looks, from aesthetics, it looks like black hole.
Right, but I mean the solutions that they construct are in supergravity, right?
Well, I mean, this is in a sense, I would call that, it is a small camp of the community, maybe the most vocal, which constructs supergravity solutions. But already 15 years ago, we said this is never going to be enough.
No, that's not what I'm talking about. I'm talking about the fact that, so the fact,
Holography, we can see what sort of geometries you expect.
no, but what do you mean by geometry? In fact, this is precisely my question. So why do you say that these are geometries if they're not classical?
Geometry outside the horizon to the aesthetic infinity, then it's classical geometry.
So, but far away, I agree.
Far away, so what it becomes, in such fuzzy is from the.
Yeah, but what do you mean by fuzzy? What do you mean by a string solution at that stage? I think it's one thing to have a statement about these states in the dual CFT, but it's a different statement to make a bulk statement about them.
You also know using ADS-CFT what is the form of the solution in the throat, because the state determines.
Yeah, I mean, maybe we can talk about it, but I think the statement that I wanted to make was this particular point, which is that if you are in the quantum string theory regime, I don't know what it means to say that space-time caps off at the horizon. I don't know what operationally that means.
So this means that there are expectation values of the operators whose size is of the horizon size, and all the explicit possibles. Actually, you can check it a posteriori.
Go on.
You can do the ADS-CFT computation for beauty expectation values in the specific state, and then see what is its size. And the size turns out to be the size of the horizon of the same geometry.
Yeah, so I don't think there is I think this statement depends on the operators that you're looking at. I think it is not obvious to me that there is a universal statement that applies to all operators which you can make regarding things at the horizon. So anyway, I think maybe it's better for us to, this is not my, my hill to die on, but I think that this is, I probably would disagree with you even after we have this conversation, what I feel, but let me just go ahead and at the end maybe we can talk. So, yeah. Yeah, I think that should be enough. Thanks. So many of these rest of the slides are pictures, so I think I'll be like flying through them. So, so the point I wanted to make is that perhaps we can simply chop off the geometry before the horizon and as a toy model for a first ball and see how the modes behave. Okay, so this is something that we can try to do. And so this would mean that we would be computing normal modes of a black hole instead of quasi-normal modes by introducing a stretched horizon. So we can impose Dirichlet boundary conditions, just like Toft and various other people have done back in this thing. And we'll do this for a horizon where the wave equation is reasonably tractable, which is BTC. I mean, you can do it for other cases as well, but BTC, the special functions are well known, right? So so now I will, in 2 slides, my basic setup will be clear. So you solve this is the BTC black hole. You solve the wave equation, separate modes, and I don't think there is any real explanation required here. I'm just solving the wave equation in BTC, and the key point. So the equation 6 is standard. So the key point is that you have, we demand 2 boundary conditions, one at infinity, the normalizable one, and one at the horizon, at the stretched horizon, that we demand that it is some Dirichlet boundary condition. Okay, so if you do that, so I don't believe either condition is important for the linearity of the ramp, but you will see that when you do this and compute the normal modes and compute the spectral form factor, you will find a linear ramp. So, but the reason I'm emphasizing this is that I don't think it is super important what boundary condition you impose, as long as you get standing waves and modes, whatever. Okay, so that's what that is. And these 2 conditions are enough to fix the quantum omegas as a function of n and j. And when we compute this, we find a wrinkle in the conventional expectation. While it is true that the spectrum has linear dependence on n, the dependence on j is non-trivial. And if you compute your spectral form factor, you find basically precisely a ramp. Okay, this is for generic values of, we'll have to truncate the quantity at some n cut and j cut, but if you do this, this is what you find. So, and I'll show you some more plots. So, okay, so hopefully that was not too fast. There's nothing going on there anyway.
Does the slope vary with the cutoff?
No, it doesn't. It is, yeah, it doesn't vary with the cutoff. So it can become kind of lost in the fluctuations as you move far away, and eventually what happens is if you're too far from the horizon, it just basically becomes a mess of fluctuations. That's what happens. So
Values numerically where you do a moving average.
you can do it, but I think it is it's not very interesting because it is. I mean, if we can do a small ensemble, you can get a ramp by doing that, certainly. I mean, I think that I mean, if you want to just see the ramp, we can do a small ensemble average. I'll show you a plot. So that I think is ensemble average over the cutoff, Yeah, so it's a very small, this thing, just to see that the slope is really 1. So because that's one thing that is supposed to be important, because you can find slopes which are far from that. The spectrum in the j direction is key for getting the ramp. The sum is over enough j's, we always see the ramp, irrespective of what ends we keep. By plotting a slope one line through the ramp, I'm seeing my slide, for the first time, so I am also kind of like, what is going on? So by plotting a slope 1 line through the ramp, we can convince oneself that it is consistent with 1. Okay, so so this is what I was saying, and so the cutoff related question that was asked, it basically corresponds to the kink that you see at the top of the ramp, and if you bring the cutoff closer and closer to the horizon, the kink becomes smaller and smaller and it goes away. Yeah, this is over. We are just to see that slope of the line clearly. We are doing an average over the stretched horizon radii.
So the height of the plateau doesn't depend on the
it depends on it depends on the cutoff in n and j, because that's largely controlled by the size of the Hilbert space, right? So the Hilbert space, this is a probe calculation. We are doing a scalar field in the black hole, so that's controlled by the cutoff we are putting in the at that Hilbert space. It's not very. I don't think it's very interesting specifically, but maybe I yeah. So anyway.
You're working with the global needs.
Yeah, that's right. Yeah.
You have a discrete spectrum to start with.
If I put a cutoff at horizon, yes. If I don't, then I have quasi-normal modes.
The quasi-normal mode spectrum itself was discrete.
Yes. Yes.
And then you are putting a cutoff.
Mm-hmm. Yeah. So I mean, I'm putting the cutoff. I can't define quasi-normal modes here with these boundary conditions. Yeah. Okay. So.
But do you have an understanding of is there a relation between the spectrum, the normal mode spectrum we are getting here, and the quasi-normal?
I don't know. We haven't looked at it. Yeah. Because these are all, once you even though the BTC, the wave equation gives you hypergeometrics. Once when we are trying to solve for omegas, it's a numerical calculation. So we don't really have a very intuitive understanding of how these different modes are related. So, but there may be. Yes.
So the fact that it doesn't depend on cutoff is a little bit surprising because the spectrum apparently does depend on it.
Yes. So, but as I said, the ramp and the plateau are very robust and generic features.
Yeah, that's what
Yeah.
So there will be some robust features of the spectrum which remains invariant.
Yeah, I think that is basically, I'll show you the shape of the spectrum.
It will be like some kind of an RG flow invariant quantity, which is very interesting.
I mean, I don't know whether it is that. Maybe we can talk about it as we go. Because I think I don't.
Think of the cutoff as some kind of sliding RG scale.
Right, but these are two different. It's the cutoff is in the background, and the scalar field is a probe, right? So.
I'm talking about the dual
Yeah, I mean. Yeah, I mean. Sorry. Yeah. Yeah, it's near the horizon. Okay, so yeah.
Take cosphenomenal mode,
Uh-huh.
known cosphenomenal mode of the
Uh-huh.
and if you try to do this,
Yeah, I think you will find the dying off, and that's it.
and you won't figure out.
I don't. I mean, I haven't tried it, but I mean that's what I would expect. Yes. Yeah. They'll just die.
Anything that you compute will die off after will.
So this is, in some sense, you can think of this as a proxy, the spectral form factor as a proxy for the 2-point function for that question. So I think I would just like Maldasena's calculation.
Okay. So have you checked if you do the cutoff, take the cutoff very near the boundary, what happens?
Very near the boundary, you get what you find for radius.
Okay, so there will be some transition in somewhere in between.
It's not a sharp transition. It's basically just the ramp just washes out, basically. And in fact, you can do this calculation without any horizon because we wanted to make sure that this was with respect to, the horizon was the thing that was causing it, right? Otherwise, it's just a pointless calculation. So if you do it without the horizon, you actually you don't find a linear ramp. You find, depending on the situation, depending on the case and the various geometry, etc., you might find some ramp-like structure, but they never have a linear, slope 1 ramp. It doesn't happen.
Sorry, what you were saying was arduous, but this is something like putting a cutoff is similar to like a 2 bar.
I think that's more like a UV cutoff, right? This is more like an IR cutoff, like he was saying.
More putting it on a lattice.
Yeah. Yeah, it's more like that. Yeah, so so these are some generic facts about the ramp that people often say. So a ramp of the slope 1 in the spectral form factor is, before this calculation, I don't know a single calculation where the what was asked also. I don't know whether there is a real answer to that. So because the only case where without a direct RMT you can see this as spectral form factor having a linear ramp is this calculation. And typical integrable systems have no ramps. We can check it very easy. And one may find a ramp, but without a slope 1 by doing an average over random couplings in integrable systems like SYK2. Okay, SYK2 is integrable, but if you take a random coupling J and then you average over that, you will find a ramp-like structure, but it doesn't have slope 1. A surprising thing here is that our system does not have a conventional Revel repulsion, as I will show you in a second, and is therefore, at least not technically, it is not an RMT, even though towards the end of this talk I will connect with some RMT thing.
The equation that you're solving is just, you can just write a hypergeometry.
Yes, yeah. It's just hypergeometric near the horizon. Yeah. Yeah, yeah. I mean, equal to equal to 0 in some. Yeah, yeah. We are putting a Dirichlet condition. Yeah. And we have also checked. I should also say that we have actually checked it also for Rindler with a cutoff and a compact. This thing. I don't think it is. And even there, the structures that I'm saying here are exactly parallel. So I think it's a universal feature of cutoffs around horizons. So so the spectrum has interesting structure as a function of J. So this is answering the question, and this is Ian's question. And the level spacing, if you include a lot of n's, we have n and j. So if you include a lot of n's, it basically looks Poisson superficially. But if you just look at for one value of n, many values of j, you find some sort of a strange structure. Okay, we didn't have enough resolution in the last paper, the first paper that we wrote, in order to get, look, you can see that it's a bit choppy, but the structure is correct. So we kind of speculated in that paper that this might be interpreted as some sort of an extreme version of a Wigner-Dyson thing, because if you kind of imagine that there is some sort of a thing going on, so maybe there's an extreme level repulsion, So let me make some asides, and then I will come to the upcoming paper. So the key point is that the compact directions are crucial. So if you just have if you don't have the compact dimension, like for instance, if you just take a Rindler without any compact directions, then you will not find this feature. Okay, it just gives you some trivial stuff. So, and I think it is ultimately related to probably why JT gravity and things in 1+1 dimensions naturally come with this ensemble. Because in order to really, if one has to see something like this, you need some J dependence. Okay, so the J dependence of the spectrum getting pulled down. What I pull down, I mean, is this thing here. So the fact that it's not linear. So, and in general geometries, oftentimes it is linear. Horizon was key for the emergence of the ramp. In ADS as well as flat space with the whole box, the spectrum has linear if the spectrum has a linear dependence on J, and this prevents the ramp. Yes, you can check fairly easily. And so yeah, we expect that this is a fairly universal feature of horizons as long as there are compact extra dimensions. The results are qualitatively identical for Rindler times a compact space, where also the wave equation is solvable in terms of well-studied special functions. Okay, so we haven't done it for higher dimensional black holes, but I think it will hold there also because the the radial solution is some Hoyne functions and they're less studied. Okay, so is that a question? Sorry. Okay. In the semi-classical approach, the ramp in SFF this ties back to some questions which were asked earlier. The ramp in SFF is thought of as a result of including these replica wormholes and so on, and you expect a smooth ramp. This is Suresh's question. So you expect a smooth ramp. But if in a true quantum gravity microstate, you expect that there would be these fluctuations. And the dumb thing that we did gives you both in one shot. So this is somehow, it's like a crude approximation, but it captures some small feature of quantum gravity. Okay, so the crucial question then, so this is sort of the stuff till our last paper. So the crucial question then is, can we get conventional Wigner-Dyson-like level repulsion and not just this sharp thing that we see here by doing something to this? And the answer happens to be yes, and it is something again we are doing based on motivation from first ball. So what you do is, instead of putting this phi equal to 0 at the stretched horizon, a sharp Dirichlet condition, what you do is you take the boundary condition to be phi naught of theta. So some profile at the stretched horizon. Okay.
Yeah, I was going to tell you that the direct possible stuff on so
yeah, exactly. Yeah. So and so this phi of so this thing. So with this generic profile, if you do it, and you can, so how do you define genericity? The simplest thing you can do is you can take phi naught of theta to have some Fourier series where the Fourier coefficients you take to be random. I think there are probably better ways to do it, which are more motivated from some sort of typicality in the Hilbert space of these scalar fields or something. But this is the dumbest and the simplest thing one can do, and that's what we did. And then as the variance, so once you define a Gaussian distributed phi naught of theta, you can talk about this variance and how you move its variance, as increase the variance, decrease the variance, and so on. And as the variance is tuned from 0, so note that when the variance of this Gaussian is 0, we are essentially in the situation of our previous paper. Okay, so we are basically at phi equal to 0. And as the variance is tuned from 0 to large, the level spacing distribution goes over from this extreme version that I showed you before. With this plot here is basically the same plot as this plot here. It's just that it's showing a little bit more of the axes, that's all. Okay, so and yeah, I mean that's not completely true because I think it's slightly different systems, but it's essentially the same. Okay, so that's the 0 variance case, what you find for the level spacing distribution, and then you slowly increase the variance. Immediately you start finding things like this, which is basically you have a level spacing distribution. This is a GUE fit. And I don't think it is very meaningful to distinguish between the various, Gaussian unitary, orthogonal, etc., etc. The reason is that increasingly what they do, for instance, orthogonal versus unitary versus symplectic random matrices, what it basically does, it makes the peak sharper and sharper and pushes it to the right. And in fact, what we are finding in the case when there was no variance was the thing which is, a delta function separated from the origin. So that means that this is, you should not take this GUE, etc. very seriously. I think it just means that by adjusting the variance, you can get things which look like random matrices. That's all I'm really, more like random matrices. That's the only point. And if you take the variance to be really large, then you end up finding Poisson distribution like this. And you also see that the ramp vanishes. Okay, the ramp goes away when your variance is sufficiently large, and it just basically becomes this. So, and this ramp case and this Poisson case are for the same values of the parameters. Yeah. Let me also just thank my friend for my collaborator Suman, who I was yesterday traveling for some personal reason, and he's the one who made these figures in the last this thing. So I should specifically mention that because it's yeah. Anyway, go ahead.
I should have asked this story before. Where does the run start? What is the scrambling time?
That is maybe I think you should answer it.
So the scrambling time is not usually defined in terms of the spectral form factor. So for example,
So let's say I just declare the RAM start.
yes, so when the RAM starts, usually that is that time scale we will call essentially where the random matrix features start appearing. So
But in this cutoff model, what is the time?
how it scales with
Yeah, what physics sets it?
oh, so that depends on that scales with the Hilbert space dimension, basically. So
No,
here, for
this
example,
cutoff BTC model.
I think what he means by the Hilbert space size is the cutoff in J and N that we put.
Oh, okay.
Yeah, I think.
levels in spectrum you keep. Suppose that I call my dimension of the Hilbert space, and if you keep changing that, then the starting point of the ramp will start moving.
As you increase it moves, it gets delayed.
If I increase, then it happens faster. So that's exactly what happens in random matrix also. So the scaling is like 1 over Hilbert space dimension raised to some power.
Yeah, I think so. Yeah, we haven't studied it in great detail, but roughly I think we have. I think we had some statements about. I think you made some statements about it in the last paper. Yeah. Okay, so so I'll just conclude with 2 more slides essentially. So I'll talk about the RMT takeaways, which is there are a few here, but this is kind of a exhaustive list of things that we have thought about RMT. But there are many things about black holes, which I think there are many things we can talk about, and I have listed only like a couple in the next slide. So this is RMT is somehow like this. These are the things we can talk about. So for instance, yeah. So the general expectation was, or at least is, I got into an argument with somebody about that linear ramps cannot happen unless there is a Wigner-Dyson level spacing, and that is just not true. You know what I'm saying? That is just not true, because we can see that maybe some sort of deformed level spacing distribution which is very sharp, you can still see it, but we can see it is what I would say. So, but it is just not true that the standard Wigner-Dyson or these generalized discrete symmetry generalizations of this Altland, the Cern-Bauer classes, there one can expect this is the standard wisdom, but it's just not true that it is the only place where you can see it. So our approach basically provides a simple and general way to generate counterexamples to this, and we have some tentative sufficiency conditions for when a deterministic sequence of real numbers, which can be interpreted as eigenvalues, can give rise to ramps. But all of this is somewhat, we are playing around with some examples and so on. I don't want to make too many concrete statements here, because I think I might change my opinion later. So, some intriguing observations about simple harmonic oscillator. For instance, one very interesting fact is that one easy way to generate, a ramp which is not linear, but has some slope which is t to the 1.4. So in a log plot, it will look like a linear ramp, but it will not be 1 slope. So that it's a very, I don't know whether this has really been looked at, but you just add noise to the levels of a harmonic oscillator and you compute the spectral form factor. That's what you would find. And I think that's like a linear ramp with any noise. We have played with Gaussian, but I don't think it matters. I think any form of, even uniformly distributed should work, is what I think. I think I might have even tried it, and I think it works, is what I think. Okay, so this is somehow the Gaussian, some of the harmonic oscillator is kind of like a, it's a strange object, right? I mean, if you compute the level spacing distribution of the harmonic oscillator, it looks like it has some form of trivial level repulsion, because it doesn't have, it's a delta function at some particular point, particular value of level spacing. So that makes it a little bit of a strange object, and maybe that is the reason why that happens, because you do find a nice ramp, but that ramp is not of slope 1. Yeah, and so there are various statements about various things I can say here. The linear ramp may be a more, so right now my feeling is that the linear ramp may be a more robust diagnostic of underlying chaos than level spacing data. Okay, so this is This statement again, I mean, it's somewhat speculative, but I think I believe it at the moment. So the more interesting thing, at least from my point of view, is this black hole questions, and so I mean, our result can be viewed as sort of encouraging for the first ball program, but it's not clear to me. But the real challenge in my view regarding the first ball program, even though Costa seems to disagree, is that it is ill-defined as a proposal for a full quantum microstates. Okay, so that's what I feel. I mean, but yeah, I'm open to change my mind. Because most of these solutions that people construct seem to be classical. So I would really like to have a very precise notion of what it means to have a quantum first ball. Like maybe it is for probes, maybe it is for some way of characterizing it. Yeah. I mean, this is clearly I'm not an expert. I mean, there is definitely room for fine tuning my statement here. I might be being too harsh. So right, and yeah, but so the only thing I would say is that I would like to have a specific statement about what kind of probes will see what. That's what I would like to see. If that can be said about or a bulk statement, that would be very interesting, I think.
I mean, it's similar to what, in the sense, you have canonical versus microcanonical. How do you distinguish it from state?
No. I'm talking about.
State. Okay, that depends on the details of it. For most purposes, would be exactly the same as expectation value in the thermal state, but there would be differences depending on the microstate.
Yeah, no, I hear you. I hear you. I'm sympathetic to what you're saying. Yes. So, right, yeah. So, So, I mean, if that is the case, I mean, we should talk about that. So, I don't want to make it more stronger statement. So, yeah, but unlike the critics of first ball, I find even the heuristic idea interesting. So that's, I think, the point I wanted to make. Because the heuristic idea that geometries chop off at the horizon, it may be interesting and stimulating for doing some interesting, intuition for how black holes work. So, and perhaps our calculation is a hint as to how to give an operational definition of bulk quantum microstate finite temperature. Okay, that's speculative, and many more open questions, etc. And that's where I'll stop. Thank you.
Time for questions.
Okay, this is more of a comment. So
Yeah.
there's a paper by Preskel and Tang, but in a slightly different context. They define quantum pseudo-randomness in a very precise way.
Yeah.
And they were trying to, of course, understand in what sense the encoding in Hawking radiation can be sufficiently complex or has exponential complexity. And so
I would say that it is probably like like a sledgehammer to crack our problem. You know what I'm saying? Like it's a peanut in some ways in that, because I'm just working with all I need in my case in order to make a statement about generic scalar configurations is a notion of genericity in the Hilbert space of scalar field, right? So in that sense, it is kind of a trivial.
No. What I was basically saying is not. I mean, whether quantum pseudo-randomness can also give a linear ramp is probably unknown. Because it is well connected to black holes, one could probably try to look at something like that and see whether at least pseudo-randomness gives you a linear ramp or not. It's just a comment. And
I have to think about it. I don't know whether. I don't know. Yeah, Onkar may have some comment on that. I don't know. Yeah, please go ahead.
How should I think about your calculation? So if I were interested in computing the spectral factor from the CFT point of view in an ADS CFT context.
Yeah.
So should I think of your calculation as giving like the bulk quantum correction?
In some, but it's highly heuristic, obviously. Okay. But this is the way I was thinking of this calculation is as sort of a bulk mechanism for how you can see it. You know what I'm saying? I mean, but it's quite heuristic, obviously, because you're just chopping off the geometry. We are breaking diffeomorphisms. Everything is, the only thing that I think is going for the calculation is its simplicity. So other than that, I think there is, you can, there are various problems with it, right? I mean, clearly. So
heuristically, I was wondering whether, oftentimes if you compute things from the CFT point of view, there is a sort of order n squared term, which is classical in the bulk, and then there's a bulk contribution, which is
right. So, but I think when you chop off in the bulk like this, it is not very clear how that happens, I would say. Right? I mean, it's an uncontrolled calculation in that sense, right? I mean, we are basically talking about. So I'll just repeat what I said, which is that I think the only point of the calculation in some sense is a simple calculation, and in that mechanism somehow seems very transparent in some way. That's all I can really say.
Thank you.
Yeah, it's a probe, but also we are putting a cutoff, right? I mean, the boundary conditions are highly non-trivial in some sort of conceptual sense, even though it's a simple boundary condition, but it's a very non-trivial boundary condition conceptually from a CFT point of view. Yeah, exactly.
How do you view the this island in this fuzzball picture, since there is no
yeah,
information loss?
that I think you have to ask more fuzzball picture. Hint, hint. I really don't know. I mean, I have, yeah.
Okay, any more question?
Okay.
Okay, if not, let's thank Chethan.
Thank you.
Let's thank all the speakers of today's session.